So, good morning, everybody. I am Paramet Virasanti from Chiang Mai University, and I am the chair of this session. I would like to welcome you all to this session in this morning. In this session, we have 5 papers, but we will change the order of the presentation. So the first one, we will start with the second paper and go to the 5th paper. And the first paper will be end of the session. So for the second paper is a video clip. So the organizer, please show the video clip of the second paper, State of Health Estimation, please. And after the video clip, we will have a discussion. So please play the video clip.
Okay. Good morning, everyone. My name is Panavapiancha. I am master student majoring in electrical engineering from School of Engineering, King Mongkut Institute of Technology, Lat Krabang. Today, I would like to present about state of health estimation of lithium ion phosphate battery using DC internal resistance and neural network. Okay, I have divided my presentation into 4 parts. First is the introduction. Second is experiment. The third is result and discussion. And the last one is conclusion. Okay, let's go to the first part. Is the introduction. Currently, renewable energy sector has rapidly grown. Therefore, electric vehicles are become popular. There are plenty of electric vehicle companies instead of internal combustion engine. The battery is the most important component of electric vehicle and energy storage system. So, battery needs to maintain and estimate the battery life or state of health all the time. At the present, there are many types of the lithium battery. The popular lithium battery that can use in various applications is lithium phosphate, since it has a long life for use and high efficiency, high safety. So we choose this battery to study. Our objective is to use the battery parameter value to estimate the state of health of battery. Okay, the state of health of battery is the indicates about the battery life. By this experiment, measure the state of health of the battery with the equation on the slide. C is the capacitor of the battery, and the C value we use a Coulomb counting method to calculate the C value. The state of health method. From this slide, there are several methods for estimate state of health, and I selected the artificial neural network here. I will talk about why I select this method. For the advantage, online estimation method, efficiency, the capture of nonlinear characteristics and good accuracy. Next, go to the experiment. It is the simple lithium battery model that consists the resistance and capacitor. From study found that when the battery has deteriorated, the resistor zero value will change too. We are interested in the DC measurement. We select the data from the battery management system of the battery. The provided data consists the current, voltage, and the time used. Use the difference between charge voltage and discharge voltage to calculate the internal resistance according to the IEC 62620 that can be measured online without take the battery out of the system. Okay, then move focus on another percent of state of charge by correlate difference of charge voltage and discharge voltage to the internal resistance. The blue line is the charge discharge voltage at the 100% state of health, and the red line is the charge and discharge voltage at the 80% state of health. We found that there is a gap between them which can indicate internal resistance and can conclude the gap of 80% state of health is wider than a 100% state of health. That means there is more internal resistance. And this graph shows the relationship between the internal resistance and the percent of state of health as well as the state of charge level. It is noted that as the 40% to 60% of state of charge are the same trend. So we select the diagram to determine the battery internal resistance. Next, come to our experiment. We collect the data from the life cycle test 2-pack of the 40x voltage and 100 amp-hour lithium-ion phosphate battery were charged with the 60 amp constant current, then take the time for rest and discharge with a constant current of 100 amp, repeat 300 cycles. This figure is the battery testing equipment, which consists the electronic loads, power supply, and controller. Okay, and this is the battery test circuit diagram. Next, show the artificial neural network process to the estimate state of health of the battery by using the relation of the internal resistance of the battery 1 train until you got the acceptable error value, and then bring this model to test with the parameter width of the battery 2. Okay, in this research, the artificial neural network was developed by the MATLAB. Inputs and outputs are DC resistance and state of health respectively. The property of the artificial neural network model are as follows on this slide. Okay, next we are looking at the result and discussion. Life cycle test result, the graph shows that the battery capacity grows during the first 10 cycles. It grows up, then fall until the SOS value is approximately 84%. In this study, the battery capacity was reduced by close to 80% state of health at the recommendation value for the battery maintenance. Another graph shows the relationship between the DC resistance and state of health. The relationship are relatively related but nonlinear. Therefore, artificial neural network was adopted and estimate state of health. In this figure, average the validation RMSE lower as the number of the epochs, like within 200 epochs to got the acceptable error allow 0.11, and it shows the adopted neural network can quickly learn to the relationship between the DC resistance and state of health with acceptable error. The state of health estimation result of the test data after the train process is shown in this figure. Although the phase cycle is a cycle 50 to cycle 150 is have a significant error value. The predicted state of health match actual state of health value quite well in a high number of the cycle. It's cycle 150 to 300 cycle. Okay. The result of the calculating of the error of the test data after the train process is shown in this slide. The result show the MEA is less than 10%, the MSE is less than 2%, and the MSE is less than 15%. Therefore, the errors are acceptable. Okay, let's go to the final part, the conclusion. The results show the trend of state of health is declining when the battery is used. Also, consider the relationship of the internal resistance of the battery by the DC resistance method that can be measured online. To recommend state of charge range to measure battery internal resistance is 40% to 60% state of charge. Therefore, the state of health estimation was performed using the artificial neural network method for describing the nonlinear relationship. As the result, the error value is acceptable. Therefore, the artificial neural network model can predict the battery life in theory. Okay, for suggestion to reduce the error value, additional the study of the relationship of another variable related to the battery state of health, such as the temperature change. Okay. Thank you for your attention. Anyone have the question?
So thank you for the clip. Mr. Panawat, please show you up.
Yes, I'm here.
Okay. So, are there any questions from the audience? So, maybe I have one question. You can correct me if I'm wrong, Mr. Panawat. If I understand you correctly, you have two sets of battery, right?
Yes.
And the first battery you use for the training data, and the second one is for the testing data.
Yes.
Okay, so I have a question regarding the first battery, the results that you calculate the SOH and the life cycle. Have you validated this information with the manufacturer or anything else? The data of the life cycle test and the cycle.
The battery is from the factory in China. I cannot tell you the it cannot show you the invaded and the information of the battery. Okay, I cannot. Can you ask me the again?
Okay, I'm asking you the question regarding the validation of the test training data. maybe if you can look on the slide 25, yeah, it's a graph of SOH and the cycle of battery. So I ask you that you have the evaluation of this information or not. I don't know.
Okay, I understand. The state of health we can calculate from the Coulomb counting to check the state of health, to check the capacity of the battery, to make sure that is the true capacity of the battery.
Okay, then maybe I give you an recommendation. The first thing what I see here in this graph, what I'm wondering is about the cycle and the SOH. I see that only 300 cycle, but the SOH is dropped to the 85% SOH. For me, it seems strange. This is the first point. Maybe in the future it would be great. Maybe you can compare with you have to validate this information first, maybe with the manufacturer, or maybe compare with the slide on slide 17. I don't know how you get the information of the slide 17. Maybe it would be great for you in the future. Okay, then thank you, Mr. Panawat.
Okay, thank you.
Okay. So we move to the second paper, actually the third paper. The paper name is Phase Balancing Improvement in Unbalanced Medium Voltage Distribution System. So this is a video clip as well. So the organizer, please play the clip.
Good morning, everyone. Today I want to share you about my topic is phase balancing improvement in unbalanced Humvee distribution system. Represented by the Indara. For the outline, we have 5 points. The first point is the interaction. The second is objective. Third is methodology, and 4 is result. And final point is the conclusion. As you can see in figure 1, example of traditional unbalanced distribution system. Generally, power from the substation transmitted by the three-phase line that can be connected with the three-phase transformer as like 1 and 2, or connected with the two lines that as 3 and 4. And 5 and 6, we have the single line. There are several problems that can be solved in this part. The problem has been increased load demand, unbalanced load, and the large power loss, and the unbalanced voltage profile. For the solution of this paper, we want to study about phase arrangement of the transformer connection by using GA to minimize the power loss and improve voltage profile. Objective and constant. For the objective, we want to minimize the power loss based on this equation, and the constant we have to set a tolerance value between 10% and voltage of each bus between the minimum or maximum voltage. For methodology, we have 2 parts. The first the first part study on the power loss, and the first part we have 3 cases. The first case be arrangement with the original line, and then minimize the power loss. For the second case, we add single line to the B line, and then arrangement based on power loss. For the case 3, the system have the complete C line and then arrangement based in. After we arrangement, we compare and find the minimum power loss from each case. For the part 2, we use daily load consumption. So we insert the profile and insert cost of electricity. In this case, we want to compare basket between the case 1 arrangement with the main line running with the 24-hour and then get the energy loss. After that, we compare energy loss between basket and case 1. In this slide, we want to study about concept of connection of primary transformer. Step 1, arrangement C connection primary side of transformer. If we have the 3 line ABC, we have the 6 possible connection as the example like this. In concept 2, arrangement 2 line connection primary side of the transformer. Example, phase A and phase B, we have the 2 possible connection, AB or BA. For the case 1, we arrangement with the original main line. In this case, we focus on the 2 line and 3 line, and then apply concept 1 and concept 2 for arrangement. You can see the first detailed flow chart in the right side. First, we need to need data and line data, bar data. Insert concept 1 and concept 2 for the condition. We check the 3 line and then apply concept 1 and check 2 line and then apply concept 2. After we complete it, we will get the power loss as the energy power loss to the objective of GA, and then go to GA, minimize for case 1. For the case 2, we'll first arrangement based on add single line to the 2 line. Example, in F1, we add single line into the transformer 1, 3 and 4, and then we got the 3 line, new 3 line in 3 and 4. For the system, we know after we add it, we get the 3 line and single line. For the case 3, we add 3 line, we complete the 3 line with the new topology. Example, we add 1 line with the 2 line and then add the 2 line to the single line. In this slide, we detail about daily load consumption. We have the 2 curves. The orange curve is the real power in percent and the reactive power in percent, and we record every hour. For the price of electricity is the $0.132 per kilowatt hour. and then apply cast 1 compared with the best cast, and then minimize the energy loss. Testing system, we tested on the unbalanced system IEE 30 bus, and then with the supply voltage for 0.16 kilowatt with the voltage limitation between 0.9 to 1.1 per unit. With the this system, you can see it has the 3-line, 2-line, and single line with this system. Assumption, regulator or generator or transformer don't use it in the system, so we assume it with the line and use linear load flow for analysis. For the unbalanced system, IE 70 bus with the supply voltage 4.8 kilowatt and with the voltage limitation between 0.9 to 1.1 per unit. For this system, we have the system with 3 bus. Assumption with are the same in IE 30 bus. For the result of this part or part 1, we have compared the bus cast 1, and cast 2, and cast 3. You can see in IE 30 bar, we have the cast 3 in the bus cast. So we got the power loss as 34.89 kilowatt with the loss reduction to 24.09%, and the time compensation with the 13.68 seconds. In the topology IE 70 bus, 31 bus, we have the same result of cast 1, cast 2, and cast 3. So in this case, we know it has the 3 line completed. So the result of this case will be the same. The result based on energy loss, we compare with best case to case 1. So the case 1 is the best compared with best case. So I is the best because the result of energy loss like this 31.34 megawatt hour per year, and energy loss cost within 19.19 USD per year. And with the topology IE 37 bus, we have the energy loss with the 122.84 megawatt hour per year, and with the energy loss cost with the 16.21 kilo USD per year. So in this case, we have the case 1 is the best compared with the best case. For the conclusion of future work, after we complete the implementation testing system according to the result, there have 2 points. First one, bus arrangement can be minimized the power loss, and the second one is the voltage is path stand within the tolerable level. For the future work, to improve the algorithm search for minimize the energy loss within with investment cost, including distributed generation integrated integration. For the final of future work, I want to implement the proposed GA as well. It improvement to test real system for the unbalanced distribution, power distribution system in Cambodia. For attention, if you have any question, you can ask me later.
So thank you very much, the presenter, Mr. Dara M, right?
Yeah, I'm here, sir.
Okay. So, are there any questions from the audience? You can turn on your microphone and ask directly, or you can type in the chat box as well. Is there any question, please? So, if no question, maybe one question from my side. You propose the rearrangement concept to manage the unbalanced system in the distribution, right?
Yes. Yes.
Okay. I have a question regarding your simulation results. You have test with two test systems. The first one is IEEE 30 bus, and the second one is IEEE 37 bus. For the first case, the result seems correct that the case 3 is the most improvable from the power loss.
Yes, yes.
And the second one, for the second case, maybe can you comment why the power loss is all the same for the 3 case?
Because the I3 for E13 bar has the complete system 3 line. So we use only case 1. Yes.
It means the 37 bus is 3-phase system, right?
Yes.
Okay, and the 13 bus is not a completely 3-bus system.
Yes.
Okay. So then, that's all from my side. So thank you, Mr. M. Dara. Okay.
Yes, thank you.
Thank you, thank you. So then we move to the third paper, the optimal network reconfiguration with DG placement and sizing in distribution system using SOE and GA. So this one is also a clip as well. So the organizer, please play the clip.
Greeting all committee. Today I would like to presentation my paper. Title is Optimal Network Reconfiguration Net with DG placement and sizing in a distribution system using hybrid method SOE and GA. Presented by Sok Lee Pieng. Outline, we have first introduction, second methodology, third test system, four result and discussion, and five conclusion. First introduction, in MV distribution system are built in mass and operated in radio structure. Network reconfiguration system is an operation to alter the topological structure of distribution feeder to change open or close signalizing switch and tie switch in order to obtain the radial structure. DG integration into distribution system can reduce power loss and improve voltage profile. Optimal distribution system architecture with DG integration is challenging to minimize the loss value. Next, third objective for this paper will be use the minimize real power loss as the objective and improve voltage profile. To achieve the research objective, the author was proposed two cases. Case one is using topology structure obtained after reconfiguration network to placement and sizing of DG. Case two, simultaneous reconfiguration network with setting and sizing DG. Methodology for case one, using the topology structure obtained after reconfiguration network to search placement and sizing of DG. Start using the initial topology structure obtained after configuration network. Use GA to search the location and sizing of DG. Run load flow to calculate the loss value. Check the objective is minimal. If the objective is minimal, implement sequentially switch opening. In step for reconfiguration to obtain a radial structure. Then show result. Stop. For case 2, simultaneous reconfiguration setting and sizing of DG. Start, close all tie switch in the system to convert the topology into a mesh system using GA to search the location and sizing of DG. Using sequentially switch opening, check the minimum objective value. If the objective is minimal, so the result, then stop. For SOE algorithm, step 1 of SOE is sequentially switch opening used for reconfiguration network. Start, read the data, bar data, line data, or switch set to normal close. Open one switch in the topology and calculate the load value and record the value, then close the switch open. Do it until all the switches in the topology have been moved back. Find the smallest loss value, then check the radial system. Is it radial system? Then stop. Objective function and constraint of SOE. Objective function, search objective is minimize power loss, and constraint is bus limit. I choose voltage is 10% tolerant, and limit current is current should be less than maximum current, and radial topology structure is done by number of bus minus number of break equal 1. Third, test system. For this paper will be test on two systems. First one is IEEE 33 bus system that have supply voltage is 20.66 kilowatt of kilovolt, and the real power loss is 202.67 kilowatt, and the tie switch are 33 to 37. For another tie system is IEEE 69 bus system. The supply voltage is 12.66 kilovolt, and the real power loss is 226.644, and the tie switch are 69 to 63. For DG integration, in the problem we will be inject the 3 DG into the system, and the limit of DG will be increased from 0 to 2 megawatt. For result and conclusion, for test system IEEE 33 bar result, we obtain forecast is for 57.34 is lower than another method, and the tie switch is 7, 11, 14, 32, and 37. For the location of DG is on the bus 8, 24, and 30. And for the sign are so separately. For case 2, we obtain the power load 50.72, and the tie switch are 11, 28, 31, 33, and 34. For the DG sitting on 17, 25, and so on. For the sign have been sold separately. The result got better than another method. For test system IEEE 39 bus system, we got the power load is 35.88. Is slightly bigger than another method, but the voltage we obtain is improved equal another method. And for case 2, we obtain the power load is 35.67. And for for the sign have been sold separately. The result got better than another method. For test system IEEE 39 bus system, we got the power load is 35.88. Is slightly bigger than another method, but the voltage we obtain is improved equal another method. And for case 2, we obtain the power load is 35.67.
Sorry, Professor Paramesh, I think the clip video has some problem.
Okay. So then we can stop the clip video at this
Yes.
point. So no problem. So then the presenter, Mr. Sok, and I cannot spell your name. What's your name correctly?
My name's Soklip Professor.
Soklip. Okay, thank you.
Yes.
So, any question from the audience? It's about the network reconfiguration with the tie switch. Any questions from the audience, or can type in the chat box for the questions? So if there is no question, maybe I would like to ask you some question. If I understand you correctly, you have two states. The one state is you find the DG sizing and location, right?
Yeah.
The second one, you try to improve the power loss with tie switch.
Yes.
Okay. The first thing is very hard to follow what is different from case 1 and case 2. But if we look on the test system, maybe we're talking about only the 33 bus system. So the first question is, you mentioned that the tie switch on the 33 bus system is switch 33, 34, 35, 36, and 37. But from your results, the tie switch is changed. Maybe for the case 1 is 7, 11, 14, 32, and 37. How come the 7, 11, and 14 switch here?
That's 33 to 37 bus is for the bicycle, but the 7 the I saw in the thesis is high switch 10 from the reconfiguration. I use the topo structure of 10.
I cannot hear you or something.
From
Okay, I cannot hear you. The signal was lost. Okay. Maybe from my recommendation, you should I think you should point out correctly what do you want to study. Maybe you use the topology with the DG and sizing and fix this topology, and you try to do the reconfiguration and compare what is the difference. Maybe it's better. Because if I look here, for me it's quite confused. You have two states and you have different scenario of DG and sizing, DG sizing and location. So it's hard to compare for the results, from my opinion. Maybe you should fix something and prove that you are going to improve something. It's better.
Thank you, Professor.
That is my recommendation. Is there any question? So if no question, we move to the next one. The next paper is multi-objective optimization with two-state design approach of IPM model for compressor application. This one is also the clip as well. So then,
good morning, everyone. Today we are going to present the multi-objective optimization with two-state design approach of IPM models for compressor applications. This presentation was created by me, Mantana Zantanan, and my partner, Apisala Shinban. This presentation takes 10 to 12 minutes long, If you have any questions, feel free to ask at the end of our presentation. The outline of the presentation is composed of 5 topics. The first topic is the introduction. The second is the literature review. Then the methodology. After that is the results of the project. And the last one is the conclusion. This project is improving the design of IPM models for use in compressor applications in air conditioning by utilizing a multi-objective optimization on slit design patterns on the loader of IPM models. The IPM model designs are conducted using the genetic algorithm and the finite element methods, with the purposes to state design process to simultaneously optimize torque level, cooking torque, and efficiency. The advantage of the slit design for optimization are the low production cost, compatibility with the existing control system, the effectiveness of reducing torque level, as well as improving the efficiency of the original motor design, and reducing noise and vibration in the motor. A permanent magnet motors, or PM motor, is an AC motor that incorporates or attaches magnets to the loader surface and is classified into 2 types: the interior permanent magnet, or IPM, and surface permanent magnet, or SPM. Permanent magnet attached to inside the loader generate magnetic flux in both types. Refer to popularity of choosing a motor for decades. The market for permanent magnet motor was dominated by surface permanent magnet, or SPM motor. However, the growing hybrid and electric vehicle markets have increased demand for internal permanent magnet, or IPM motors in recent years, with features like near constant output across a wide speed length and magnet retaining architecture. So, IPM motors are an excellent choice for traction and auxiliary motor applications. Okay, let's move to the next topic, methodology. For methodology, we used IPM motor type to optimize. The geometry of the nominal design IPM motor under consideration are shown on the slide, where the stator is the outer part and the loader embedded with permanent magnet is the inner part. The specification of 6-pole IPM motor with a rated speed of 3,600 rounds per minute with around 91% efficiency. The total of magnet torque and reactant torque in the IPM motor is known as generated torque, influenced by the size of revolving magnetic field determine magnet torque, while the silency of IPM motor determine reluctance torque. And the ideal torque equation is given by the equation 3.1 that shown in the slide, which stands for the capital T. To maximize the torque, the parameter associated with must be optimized. However, the geometry of the motor must be optimized to reduce the torque level and cooking torque. Specifically, the design of slit pattern of the loader is considered in terms of position, size, and slit distance. The first step process, or the expert design, is the process to limit the design space. Consider case, for example, 6, 8, 10, and 12 slits, and then choose a better result for the second stage design by using genetic algorithm. To the second stage process, or the multi-objective optimization based on genetic algorithm part. The multi-objective optimization module for a deterministic optimization problem has the form of equation 3.2. In this study, 3 objective functions are considered: minimizing torque level, maximizing torque, This is the flowchart describe the multi-objective optimization based on genetic algorithm in second-stage design process.
For this figure, show an example of the graph pattern that can be obtained through optimization. The red line is an illustration of a Pareto efficient frontier, in which the frontier and the area immediately next to and below it represents a continuous set of options. The blue dot on the frontier represents Pareto optimal production decision. After the design chosen for the second stage design process, this is the table 4.2 that shows the list of design parameters to be optimized. For the results topic, result of the first stage process, the four patterns are considered and the comparative results are shown in table 4.1, where the design objective of torque ripple, and talking torque are considered. The design of 12 slit gives the highest torque. The design of 10 slit gives the smallest torque ripple with the second highest torque. Therefore, two designs of 10 and 12 slit are chosen for the second stage design process for further optimization. The dominant design on the torque and torque ripple plane for the 10 slit pattern and 12 slit pattern are shown in figure 4.1. The monotonic trends are exhibited as the motor with higher torque also produce higher torque ripple. The result also show the both 10 slit and 12 slit design give competitive performance where the Pareto lines are relatively close to each other. The efficiency of the 10 and 12 slit design are shown in figure 4.2. The design results show that both 10 and 12 slit design give competitive performance in term efficiency. However, the 10 slit design give highest efficiency at around 93.95%, whereas there are more number of 12 slit designs with higher efficiency than 93.95%. For the results, this table shows the comparison between the nominal design and the final design after optimization. The final design has improved from the nominal design a lot. In particularly, the torque ripple effect on noise problem after optimization improved about 66%. The torque improved about 4.32%. And the efficiency improved about 1.24%. This is the torque graph compare between nominal design and final design, and the red line in the both figure is the torque max or average torque that the motor generates. For conclusion, to further improve the performance of the IPM motor in terms of higher torque, high torque density, and high efficiency, the IPM motor design may result in more vibration and noise, which is caused by the torque ripple of the motor. The motor design considered in this work are focused on the position and size of the slit pattern utilizing the multi-objective optimization with two-stage design approach with GA techniques to assess this problem. The results have shown that the design with 10 slit pattern can achieve better performance that can minimize torque ripple, produce high torque, as well as enhance motor efficiency. Thank you for your attention. If you have any question, you can ask.
So thank you very much. The presenter, please show up. There are two presenters. I cannot remember the name. Please turn on the camera, please. Are the presenter inside the room? So the organizer, if the presenter is not show up, is any problem, or we can skip? The organizer, can you hear me?
Hello. I think you can skip to the next one first.
Okay, thank you. So then we move to the last paper, actually the first paper in the program. So please welcome the paper non-incentive load monitoring using multi-level perception for application classification. Please share your slide. This one is the presenter will be presented online. Please share your slide and start the presentation, please.
Hi, I am the one who gonna present the paper ID through the double five. Can I share slide, please?
Yes, of course, please. So
Okay.
maybe you can turn on the camera as well.
Now I did turn on the camera. Did you see that?
I can see your slide, but I cannot see you on.
Okay. Because
Please
maybe
turn on the camera as well.
I did turn on it, but we have to make the organizations when we present. By the way, I want to start now.
Okay.
Okay.
Please go
Thank
on.
you. Okay. My name is Chakri Sinonchhat. I am the a member of the Rajamangala University of Technology in Thanjavuri, Pathum Thani. Today, I would like to present my title. Paper is non-intrusive load monitoring using multi-layer perceptron for appearance classifications. My co-worker is Rajut Jampayun. Non-intensive load monitoring, or we call NLM, in the presentations today. Next, the content that I want to present today is about the objective, introductions, methodology, experiment and results, and also the conclusions. Let me start with the objective. The objective of these papers, I want to find out which one is the suitable multi-layer perceptron. The multi-layer perceptron is the one of the neural network, or can move to the AI in the recently. By the way, the NLM, they try to use the signal from the appearance that in the stable state. But in my site, I think that we can use the signal input from the appearance faster than that, not to wait until the stable state. So that's why I decided to use the some of the signal from the FPGA, not microcontroller. First of all, this slide I want to show that the NLM system, they collect the data of the appearance. They have many works have been done in the previous work. They wait until the appearance become the stable status, so they can recognize that what kind of the appearance have been turned on and what kind of system have been using the energy. In my opinion, I think that we can get better if we can use the faster input and can design the digital meter in the future. So that's why I try to look back in the previous work that what are they using. So they are using the power harmonics, they are using the currents, and also the wanted anything as I introduced the reference. For myself, I try to use the currents, but I not use the microcontroller to correct the data. We use the FPGA that is high sampling rate, I mean, to correct the data. The FPGA can sampling rate faster in microsecond. After that, we take the signal from FPGA change to the image processing. Then we use the cryptogram that's introduced in the paper. After that, we transfer the image processing to to be the input of the artificial neural network multi-layer perceptron, and then we can decide that what kind of the appearance have been turned on. What is the energy consumer have been using is. Of course, FPGA not the first one that have been worked in this situation in this paper. I have been working in FPGA with binary techniques. That is about 2 years ago. The binary techniques, we have to wait the NLM until they're working on the stable situations. That means all the appearance have been working in purpose already. Now I change the binary techniques to do the multi-layer perceptron. That means I don't need to wait until the appearance have to go to the stable situation, but I take the advantage of the FPGA to use the high sampling rate from that things. So as I introduced that the FPGA have been take the sampling from the appearance. I use the 5 appearance to be the input signal from the current signal, and after that we change the current signal to be the image processing using the cryptogram techniques. The cryptogram techniques that we use, we take around around 5,000 sampling of the sampling rate of the FPGA. Just when we call in microsecond, and then we take that allow 1,000 image to be the input for training and testing of the NLM system in the multi-layer perceptron. Of course, in the multi-layer perceptron, we have used many types of nodes that we have been explained in this slide and also in the papers. You can read more in that thing. This is the normal of the multi-layer perceptron of the structure in the neural network. They got the node, they got the input type, they got the output class that we can classify. Of course, this one we use the 5 appearance. That means we use the 5 class of the 5 appearance to be the output. For the input, we of course using allow 1,000 of the image processing to be the input that we take from the current signal that we take from the FPGA. This is the overall of the techniques that we use. We take the FPGA signal from the 5 appearance that include 2 types of the air conditions, 1 lamp, 1 microwave, and 1 water pump. And after that, we take the signal to be the image. We transfer to be the image by using the cryptogram. After that, we take the cryptogram image sublet to be training data and testing data. 80% of the cryptogram image we take to be the training data from the multi-layer perceptron, and 20% of the 70% of the cryptogram image we use for testing data, and the output we take to be the 5 class, and also we take the looking for the performance of the classifications or losing of the trainings. This is the experiment and result we set up with the CPU i7 with the RAM 8 gigabit. We use the FPGA from the Atela company. The spec is MAC 10M50 DAF 48 4C60. Okay, we take the sampling rate around 10 microseconds to correct the data from the output. Sorry, from the input from the file appearance. We take around the 500 sampling, 5,000 sampling of the data, and after that, we take it convert to be the image by using the CodeCam. At this point, when we compare with the power meter that have been used in the market, the power meter they try to sampling for the NLM. We compare with them, the best one that they can find, they sampling around T seconds. Again, T second. But my side, I use 10 microsecond. That means more faster than the power meter that they have been used. If we use T second to from the power meter sampling around, let's say 10 sampling, that means we have to use 30 seconds. That means we take around half minute already. But when we change to use the FPGA, of course, we can reduce the time of the taking the data from the sampling rate. This is the one of the advantages of the FPGA. For the next one is the experimental result that we have been used with the multi-layer perceptron. Of course, we changing the node with the multi-layer perceptron. It vary between 100 until 300 nodes. With the fixed layer of the 50 nodes in the one layer, the learning rate we fix at the 0.001, and then the bit size we change from 32 until 128. All the results I have it at in the paper. You can look more in the paper later on. I want to point that when we change the size from 32 to 128, we can notice that the classifications of the testing accuracy is more increased. It's more increased because of course the node it has been increased. Its training rate it has been increased. The neural network has been more clever, and then they can classify more accuracy than before. I mean that in the 32, if you can look the paper, the training testing accuracy, the maximum is around 88.8 at the 150 nodes. When we use the 50 nodes in the one layers, and when you change to the size at 64, we can recognize that the testing accuracy increased to 89.45 in the 300 nodes. And of course, when we add the band size twice from 64 to 128, and we fix the learning rate and the node at the same, we can see that the accuracy is not increased a lot. That means that the situations of the multi-layer perceptron might be come to the stable situation. It might be enough for classify only the fire appearance in these experiments. So in the testing training result, we found that the accuracy is around 87.25% with the band size 32 at 250 hidden nodes, and training epochs around 150. And of course, when we are changing the band size to be 64 compared with the 64 band size with 300 hidden node and 150 trainings, we can see that the minimized loss is around 0.3 ROOM1. That is very minimal when we compare to the accuracy that we got. And also the result of the trainings, we can find that the accuracy that we found using the confusion matrix. After we use the testing accuracy from the multi-layer perceptron as I showed in the table. After that, I use the confusion metric to find out the classifications accuracy. This is not the classification accuracy, this is a testing accuracy, but this is the classification accuracy. The classification accuracy is gonna point out that which appearance that has been used and what is the correct answer for using the multi-layer perceptron. It shows that the confusion matrix can show that the classification, the base is around 96.7% to show the classification accuracy to point out the appearance that have been trainings and testing with the multi-layer perceptron. All the details you can find out in the papers later on from this one. This is I take the result from the paper that's been published in the ECITCON also. The conclusions, multi-layer perceptron that have been used with the NLM. We try to find out the which one is suitable for use with the FPGA, and of course we try to use the FPGA and we design the circuit to correct the input data in microsecond, and we change the data to the image processing using the COOL program, and then testing the multi-layer perceptron, which one is suitable for the this appearance readings data. And also in the future, not in the future, I mean we have been working right now. We try to use the not the current input. We use the what they call the sampling, very quick sampling in the input to find out the appearance, not only the suitable state, but we try to find out in the steady state of the appearance, because the different appearance in different equipments, they have the characteristic that difference of the currents. So I mean in the future I will find out to this one and working with the FPGA and the multi-layer perceptron, and move on to the CNN. That means one card the multi-layer the one card the AI in the future. Thank you very much. Of course, I want to thank the Rajamangala University of Technology Tanjaburi to give me the chance to do the experiment, and the Natural Resource Council Thailand that give us the chance to do this. Thank you very much.
So thank you for the presentation. So the presenter is Mr. Srayut, right?
I'm Chakri, sorry, I'm Chakri.
Okay,
yeah.
But it's okay. So maybe one quick question. Could you please comment what is the application of your proposed thing?
Okay. Now we try to move on in the digital platform in the future. Nowadays we use the power meter, meter when you measurement the electrics in your home use or in the factory. That we call the analog things. But if we move to the pattern, digital pattern, we need to use the digital meter. After we use the digital meter, of course, we try to think about the save energy in your house or in your factory. That means you need to something to make sure that your equipments or your appliance are still working properly. That means you have to get something in the digital platform to measurement, to look after or monitoring to the equipment that is still working properly. So the NLM is the one of the method that been working for a long time, but that is the analog system. But my side, I try to use in the digital platform in the future. This is the one.
Okay, thank you for the comment.
Yep.
So that's all from this session. We have 5 papers here and every paper is already complete. So I would like to thank you all for the presentation and thank you for the audience as well to join this session. So thank you for today and I hope you enjoy the day. So thank you very much. I will close the first session here. Thank you very much.
Thank you.
Thank you, Professor.
ครับ
Good morning, everyone. So my name is Thongchat Gertpon from Kyushu Institute of Technology, Japan. Today, I will be your host in this session. So let's start from the first presentation. That is the optimal size of electric vehicle charging stations in distribution system with consideration of bus voltage and line capacity limit from Mr. Anand from Chulalongkorn University.
Good morning, everyone. My name is Anand Tenalong. Today, I will present optimal size of electric vehicle charging stations in distribution system with consideration of bus voltage and line capacity limits. Outline of this presentation consists of 5 parts. First, introduction. Second, proposed solution and assumption. Third, methodology. Fourth, simulation results and discussion. And last part is conclusions. First part, introduction. Nowadays, filter configuration in a residential distribution system is usually in a radial circuit, and EV charging events usually happen at home. Therefore, the high demand of EV charging events leads to 2 problems. First, bus voltage drop, and second, overloaded line capacity. On the right-hand side, the first figures present under voltage problems. Since EV charging events could increase the total load, the undervoltage impact will easily happen when the EV charging stations are installed in a feeder. For this figure, show an example of line capacity limit problems. You can see that the total load in this bus is 30.8 kVA, but the line capacity limit is only 30 kVA. This leads line capacity limit problem. Next part, proposed solution and assumption. Proposed solution. The proposed solution proposed the evaluation method of optimal size of the EV charging station at each bus in distribution system by considering the bus voltage limit and line capacity limit during off-peak and peak time periods. Assumption in this paper. First, the amount of residential peak load is calculated from design value, starting at 60% of transformer capacity, and the power factor of load is 0.85 lacking. Second, the fairness of all customers is considered by assuming that the EV charging stations are installed uniformly on each bus, and the loads are distributed equally in the distribution system. Next part is methodology. Proposed method consists of 5 steps. Start with step 1, receiving the configuration data of distribution system and voltage limit and also line capacity limit. Step 2, determining the highest load during off-peak and peak time periods. Step 3, choosing one pattern of EV charging station installation patterns that I will show you on the next part. Step 4, Determine the optimal size of EV charging station in patterns and periods. To find the optimal size, we set the objective function to maximize the total size of EV charging station. The constraint consists of bus voltage calculation, line flow calculation, upper and lower limits of bus voltage, and upper limits of line capacity. And the last step is analysis of impact after installation the EV charging station, which is bus voltage impacts and line capacity impacts. Next part is simulation result and discussion. First, we talk with test system. The test system is typical low voltage distribution system. In this paper, the test system consists of 5 parts. First, transformer with size of 150 kVA. Second, 18 buses are allocated equally in parallel feeders. Third, amount of existing load in each load bus, which is 5.6 to 25 kilowatt and 3.49 kilowatt. Fourth, voltage limit. The upper voltage limit is 1.1 per unit and lower voltage limit is 0.9 per unit. Line capacity limit. Transformer limit is set at 150 kVA and line limit is set at 76.2 kVA. For pattern in the simulation is divided into 6 cases, which are 3 cases for 1 feeder and other 3 cases for 2 parallel feeders. There are installing EV charging station at each bus in 1 feeder and each bus in 2 parallel feeder. Installing EV charging station at the beginning, middle, and ending position in 1 feeder and in 2 parallel feeder. And installing the EV charging station in all bus in 1 feeder and all bus in 2 parallel feeders. For the load profiles, the graph on the left-hand side shows the total residential load in simulation before installing the EV charging station, and this graph indicates the peak and off-peak time period. For peak time period is on peak day, and off-peak time period is on Sunday. The load distribution corresponds to PEA residential load curves. Next, the simulation results. The optimal total size of EV charging station is determined by using the objective function and constraint in step 4. After we receive the optimal size of EV charging station, the question is what is exact constraint that limit the size of EV charging station? And we also need to understand the behavior of bus voltage and line capacity limit when installing the charging station at various places. We then plot this graph to find the answer. The presentation will be divided into 2 parts. First is 1 feeder and second is 2 feeder. For 1 feeder, bus voltage consideration is considered. 2 graphs present minimum bus voltage versus total size of EVCS. In the graph consists of the EVCS at the various stages. The results show that the optimal size of EV charging station tends to increase as the installation position approaches the beginning of the feeder. Second, the voltage impact on the distribution system at the ending of the feeder is more served than the beginning during off-peak and peak time period. And third, the optimal size of EV charging station at the end of the feeder is then limited by the bus voltage limit during peak hour. Next, we consider the line capacity consideration. This graph presents apparent power versus the total size of EV charging station on peak and off-peak time period. The results show that the line overloading impact at the beginning is more served than at the ending during off-peak and peak time periods. And optimal size of the EV charging station at the beginning of the feeder is then limited by the line capacity limit during off-peak hour. This page is summary of one feeder consideration. The graph shows the maximum size of the total EV charging station in kilowatt versus various places that EV charging stations are installed. And if we consider the case that EV charging station installed in beginning, middle, ending one feeder, and the case that EV charging station installed in all but one feeder, the total optimal size of the EV charging station is quite the same. However, the optimal size of each EVCS that we can notice from the blue number in the bracket. We can see that the optimal size of each EVCS in all but in one feeder is less than the beginning, middle, and ending in one feeder cases because of the number of considered EV charging stations. For two feeder consideration, this page is for buck voltage consideration. The results suggest that the total optimal size of the EV charging station is dominated by buck voltage limit during peak time period. Moreover, if we consider the line capacity limit, the total optimal size of all EV charging stations during off-peak time period is held by the transformer capacity limit. This page is the summary for two feeders consideration. There are two highlighted results. First, the total optimal size of the EV charging station in two parallel feeder is approximately accounted for twice that in one feeder. Second, the optimal size for EV charging in two parallel feeders is less than that in one feeder when compared on a case-by-case basis. Next conclusion, and this is the last part of this presentation. We can conclude the result following these three bullets. First, for the EV charging station is installed in one feeder. The optimal size of EV charging station is limited by bus voltage limit at peak time period, but is restricted by line capacity limit during off-peak time period. For charging station is installed in parallel feeder, the optimal size of EV charging station is dominated by bus voltage limit at peak time period, but is held by transformer limit during off-peak time period. And the total optimal size of all EV charging stations in two parallel feeder is approximately accounted for twice that in one feeder. And we suggest that the charging behavior of customer might occur during off-peak time period for evaluating the impact of EV charging station installation on residential distribution system. This is end of my presentation. Thank you. If you have questions, please feel free to ask.
Thank you very much for the presentations. So anyone has questions to ask these others? So if not, I would like to ask you some questions. This is really interesting research. Also, I want to know also how frequently that we need to re-optimize the system again. If in case of the system change, maybe 20% or something like this, we need to re-optimize again or not? Can you give us some opinion about this? Thank you.
You mean the total load, right?
Yes.
Yes.
So,
yes. If we have other percentage of load of residential load, we have to re-optimize again.
okay.
And use our proposed method to determine the optimal size of the EV charging station.
Thank you. So also the I'm not sure any impact about the PV rooftop that can be impact on this this design or something like this, because you show the figure 2 is to use the line. Also some household they install some PV rooftop. Also is there impact to your method or not?
Okay, for our research now, I only focus on the load without PV, but in the next research, I will include the PV rooftop in the next research. This research is the initial for me to power system analysis.
Thank you. Also, in your test system, I saw that it's only the radial system. So if your method can apply to the system that like the ring system or any other distribution system like IEEE 13 bus standard, something like this, have you plan to consider or apply your method in this other system?
Okay, actually, in this research, we focus on the residential load, which is mostly is single line feeder, like the radials. But we can recheck the program and change some parameter to analyze the other structure such as a ring feeder. Yeah, we can, but we might change a little bit program, our program.
Thank you very much for your answer. So any others person has some question to these authors? So if not, I will move on the next presentations. Thank you very much for your research. Thank you. So the next presentation is the estimation of battery state of charge using feed-forward neural network from Mr. Omer from University Saint Malaysia, from Malaysia.
Good morning, everyone. I'm Morelli, working under the supervision of Dr. Mohammad Khairi Sak. And in this presentation, I'm going to present my work on state of charge estimation for battery-operated wireless sensor networks. I will go through some of the basics of the wireless sensor network, then highlighting the actual problem statement, which will set the stage for further investigation. Later, I will explain few critical design choices, and then I will compare them to previous research methodologies. Finally, I will present the results obtained from our proposed work, which will be then concluded towards the discussion towards the end. Wireless sensor networks are low-cost, low-power devices that are mostly powered by small batteries. The available energy on these devices is limited due to the inability to recharge or to be replaced. Thus, critical design of wireless sensor networks is required to extend their lifetime. Most of these wireless sensor networks are deployed as a sensor node or a gateway device, and they perform various operations from sensing to data acquisition and processing. Like already mentioned, the nodes are mostly responsible to sense data, whereas the gateway nodes collect and process this data to record useful information. Now, as we know that wireless sensor network deployment is mostly performed in the remote environment, therefore, in most of the settings, it provides no physical access to the device. This makes it very difficult and challenging to replace the onboard batteries. So that means when a battery dies, that is the end of the wireless sensor network node. Now, in most of the settings, energy harvesting is not possible, that means that the sensor nodes are only operated based on the available battery energy. It is also very important to mention that the batteries are highly nonlinear devices. Therefore, the energy estimation process is complex and challenging. The energy estimation ensures the design of energy-aware algorithms that are required for wireless sensor network power management. As you know, batteries come in various shapes and sizes, but primarily we can divide the batteries into two different categories, a primary and a secondary battery. The primary batteries are the ones that we can charge, and secondary batteries are the ones that we cannot charge. In this particular scenario, wireless sensor networks are typically operated on simple alkaline cells, but now the modern trend is shifting towards lithium-ion batteries. So it is important to mention that there are various battery chemistries available, such as alkaline, lithium-ion, lithium polymer-based, and nickel metal hydride-based are a few most common ones. All of these batteries perform differently, therefore it requires a complex method for its available energy estimation. The available battery energy is usually calculated by monitoring its state of charge. As the battery discharge behavior is non-linear and depends on the various operational and environmental factors, the state of charge helps to estimate the available battery energy at a certain point in time. If you look at this graph, a typical AA alkaline cell and its discharge patterns are discussed. As evident, the battery capacity or service hours are reduced at lower temperatures, whereas at higher temperatures, the available battery service hours may increase, but also impose the risk of permanent damage due to thermal runaways. Furthermore, if we follow this graph, the battery service hours change according to the discharge currents. At higher discharge current, the battery may deplete very quickly, reaching its early cutoff voltage. The cutoff voltage are used by the system designers to design applications. We demonstrated that with the knowledge of battery discharge curves at various operating conditions, the discharge patterns can be gauged and estimated. This is required for SSE estimation that is further investigated in this research. Now, some of the questions that we ask in this research are, what are some of the most efficient SSE estimation techniques for embedded platform, and how to get the most correlated and suitable features to design a lightweight and adaptive SOC estimation neural network. There are several approaches in the research regarding SOC estimation. Most of these research are dependent on the direct measurements or the adaptive or bookkeeping methods. The direct measurements method are mostly performed in an offline setting in the laboratories and is not suitable for embedded platforms, whereas some of the techniques such as neural networks and filtering-based techniques can be used towards the real-time application. The previous research shows that the techniques range all the way from simple Kalman filters to linear SOC estimation, all the way down to the hybrid regression-based solutions, each offering a different trade-off point where accuracy and complexities are directly interlinked. In our approach, we utilized open circuit voltage to record battery voltage along with Coulomb counting method to record associated state of charge and capacity. As the battery voltage remains fairly similar over a wide range of state of charge, a certain voltage value may be inadequate to recall its state of charge value accurately. So therefore, we also propose a sliding window feature extraction mechanism that includes voltage, current, temperature, and its associated SOC values to extract the features. Using these discharge characteristics in previous step, all three battery chemistries were thoroughly investigated and the feature set was extracted. We utilized a low complexity feed-forward neural network in MATLAB for state of charge estimation. It is pertinent to mention that with careful feature extraction transformation, the network complexity was reduced and the overall accuracy was increased. Furthermore, if you look at the process flow diagram, there are some of very important things to be noticed. That the correlation matrix generation enabled to use highly correlated features to design, train, and validate the network. Additionally, various transformation techniques improve the correlation index of the feature set, thus directly mapping the model accuracy. Finally, with iterative optimization during validation, the model was further tuned to reduce its complexity and increase state of charge estimation accuracy. The results clearly show that for various networks demonstrated in this research, a different combination of various layers and perceptrons per layer were used. And contrary to common belief, adding a lot of layers may not increase the estimation accuracy. In fact, in all our findings, we found that with all the right tuning, single layer architecture performed significantly well, and it reduced the complexity of the network a lot, thus making it very suitable for embedded applications. Finally, as voltage is considered the most critical mapping function for SSC estimation, the estimation error of voltage with associated values were observed. It was found that with the proposed sliding window voltage extraction and the future values were ignored, thus increasing the function fit values significantly. That increased the model accuracy. If we focus on the results obtained for lithium-ion batteries, it's pretty evident that the predicted and actual values are fairly close, reporting close to 99% accuracy. Similarly, lithium polymer batteries report the same results with highly accurate SOC estimation. Finally, nickel metal hydride batteries were also investigated in this research, and the results show highly accurate SOC estimation. The error histogram shows the variation and accuracy losses over various iterations. It can be operated that the losses are marginal and the proposed model can be applied for all three battery chemistries. Furthermore, the proposed technique accounts for a range of temperatures and discharge currents, thus offering both scalability and adaptability. It was observed that feed-forward neural network can greatly reduce model complexities, thus making them suitable for real-time embedded platforms. It was concluded that feature selection and transformation may significantly impact the model performance. Therefore, each feature set must be analyzed and transformed independently to increase the model accuracy scores. It was also observed that data split ratio for training and testing may also affect model accuracy. And for our research, the 80-20% split works the best. Finally, with proper feature selection, transformation, and model optimization, a less complex model was designed, which is suitable for real-time embedded deployment applications. Towards the end, I would like to thank University of Science Malaysia for providing the research grant and opportunities, and ECITCON committee to provide us this excellent platform to perform our research every year. I would like to welcome any questions from the audience at this stage. Thank you very much.
So thank you very much for the presentations. So Any audience has any questions to the authors? Please ask directly to the authors. So if not, I will ask my question first. So in your research is also interesting. So Mr. Omer, so why you select feed-forward neural network instead inside of this function? I used to do it before. So there is a radio basis function RBF also that might give very good performance. Also, why you select feed-forward neural network instead of others neural network? So can you hear me? Maybe Mr. Omer. So if no response, we will move next to the next presenters first.
Hear me?
Yes.
Oh, sorry.
Yes.
I think I had some mic issue. For your question, we actually also investigated the Gaussian process regression based RBF functions. And we found out that with the proper feature selection and transformation, a simple feed-forward neural network almost gives us the exact accuracy as compared to the GPR or RBF-based kernels. Because in wireless sensor networks, we have very limited power. So unlike electric vehicles or microgrids, we always try to balance the accuracy and the amount of energy consumed to calculate the values. So because it's going to be run on a very, very small powered embedded platform, so we also want to keep it very, very simple. So in our tests, we found out that although the Gaussian process regression RBF-based function performed better, but because of its high complexity and real-time operations on the wireless sensor nodes, instead of giving, because they were giving accurate information, but because the system became more complex, so it started consuming more power.
Okay.
And our number one priority was to conserve energy. So that's why we were focusing on a less complex system.
Okay, so thank you. So and also how many training and testing data set that you test in your figure trees? So you use how many percent maybe, or how many group of data set for testing and training this neural network?
So we actually worked on 3 different battery chemistries for this experiment, and we actually operated these batteries at 5 different temperatures because we wanted to replicate the wireless sensor network environment. And for all these data points, we had more than 70,000 data points altogether. So we worked on those data points. And for the total overall number of iterations, we had initially 70 simulations. And then to further optimize, we had another 30 simulations. So altogether, it was 100 simulations run battery. So there were, for 3 batteries, we had roughly 300 simulations.
Okay. Okay. So the last question is in figure 4, I see in the around 0.8, why is very high errors in this one? The error is quite high. Any explanations to this part in figure 4? Figure 4, the yellow part.
Is it the one? Okay. Figure 4, the voltage mapping function, right?
Yes.
So what happened is that on the left side, we focused the voltage mapping directly as we regard the voltage in contrast to the state of charge. On the right, this was based on the sliding window feature extraction function. So if you see the top part, the output and target, the
the error ratio is very small and they very closely fit. But if you see the bottom graph on the right-hand side, which shows the error, you can see that most of the error lies in the negative region. And it's not the positive error. So that roughly means that this error is mostly due to the overlapping or the noise. So in fact, if we most of the times designing neural networks, we for feature sets, we exclude the negative noise. So if we exclude the negative noise, the positive noise is very, very small.
Okay, so you mean you need to this is different from the noise. So you have the any process to filter the noise before or not?
Oh, yes, sir. After this stage, these graphs were for especially the voltage function, because we wanted to highlight that the voltage mapping function improved with our sliding window extraction feature, but it still had noise. So after that, it went through normalization and then scaling, and then we applied U-Johnson transform. That significantly reduced the negative noise, and that's one of the contributing factors that increase the state of charge estimation accuracy.
Okay, thank you very much for your interesting research. Okay, so I will move to the next presenters. So the topic is about safety function design in Model 3 EVSE from Mr. Panawut from King Mongkut University of Technology, North Bangkok.
Good morning, Mr. Chairman and participants. My name is Panawat Sopon Udomsit from Department of Electrical and Computer Engineering, King Mongkut University of Technology, North Bangkok. I am going to talk about safety aspects of electric vehicle supply equipment. My presentation called Safety Function Design in Mode 3 EVSE. So, let's start with overview. What is EVSE? EVSE is Electric Vehicle Supply Equipment. All of you may know as EV charger. The presentation will begin with introduction followed by EVSE safety function and a brief explanation of my design and programming. Then the test result will be verified by the EV tester. And I will end with application and on-site trials. Electric Vehicle Supply Equipment, or EVSE, is an equipment which supplies electric power to plug-in electric vehicles. The charger can divide into 4 modes. In which mode 1 through 3 are AC chargers, and mode 4 is DC charger. In this presentation, I will focus on safety function of mode 3 AC charger. EVSE safety function in my research consists of 4 parts, which are 1. Connection check. This is check whether the charging cable and the charger connected properly. 2. Non-EV access protection. This function prevents anything else apart from EV that draw the current from the charger. 3. Cable capacity detection and overcurrent protection. This is the check that the charging cable can carry the demand current. 4. Leakage current protection. This function is very important because it will turn off the charger if there is an leakage current to earth. We are talking about IEC standard plug here. We call it type 2 connector. The plug at the end of the 3-phase charging cable has 7 connecting pins. These 7 pins are different in length. The first pin is the PE or protective earth pin, and it is the longest pin. Then the second longest pin are the power pin. They are labeled as line 1, line 2, line 3, and neutral. The longest pin will be connected to the charger first. Then PP is a proximity pilot pin. It will be made after the power pin. The last pin which is the shortest pin is the control pilot pin. This CP pin is the last to connect, so the CP pin can be used for connection check. In order to check the connection, the charger circuit must measure the voltage at CP pilot pin. If there is no connection, the voltage at CP pin will be 12 volts. And when there is a connection, the voltage at control pilot pin equal to 8.8 volts. This is because there is a voltage drop at R3 that is connecting in series to a resistor in the charger. When the charger circuit detects 8.8 volts of CP pin, that means the connection is complete. Second safety feature is the non-EV access protection. After connection is complete, the charger will generate power voltage at the frequency of 1 kHz. This power is the communication protocol to talk the connected electric vehicle. The voltage at CP will be plus and minus 12 volts. Then charger will check whether that connected equipment is electric vehicle. If it is an electric vehicle, its power voltage at the negative side will remain minus 12 volts. This because in the electric vehicle there is a diode connecting in series to R3 to block the negative current flow to R3. This makes the negative power voltage not to drop at the positive power. If the equipment that connected to EVSE is not connected, the negative 12 volts will be decreased by resistor in car. In this case, this will cause diode short. The third safety feature is the cable capacity detection and overcurrent protection. In the connector at the cable end, there is a resistor called RC connected between PP and PE for detecting cable capacity. EVSE measure voltage at RC, which is called Vsense. Using for limit current charging in each charging cable. For example, RC at 1.5 kilo ohm indicate that charging cable is not above 13 amp, and Vsense that can measure is 1.98 volt. The overcurrent protection uses a CT to sense the charging current. The charger continuously measures the current while charging. Make sure that the charging current is less than the limit current of the charger and capacity of the charging cable. The last safety feature is the leakage current protection. Leakage current protection is worked by using special current transformer clamped at line and Newton to get the summation. If there is no leakage current, the summation of the line and Newton current will be zero. If the result of the summation current is different more than 30 milliamp, comparator circuit will detect that there is leakage current. This charger circuit will interrupt the charging immediately. Next topic is the design, which consists of two following points: PCB design and programming. First part, PCB design. In this diagram, show the component of EVSE, which consists of circuit breaker, AC-DC converter for power supply, microcontroller for used for control working with has component as following: relay control, used for on-off magnetic contactor, cable capacity check circuit, GFCI circuit, current sensor circuit, and control pilot circuit. Second part, programming. Program will start current capacity check of charging cable for limit EVSE. Then it will test leakage current circuit. If it cannot work properly, program will stop working. If everything is in normal, EVSE will start charging. When the EV is connected while communicating with EV and while charging, they also have protection systems such as connection check, overcurrent protection, and non-EV protection. Next topic is test result is verified using the CWAT EV100 tester. The tester will simulate all the faults to see if the charger reacts to its fault type correctly. After testing charger with EV100 tester, the result pass in every standard of tester. Voltage communication with EV in each state is in acceptable range. Non-EV access protection system and leakage current protection can work properly, and percent duty cycle in limiting charging current incorrect. The conclusion is the application in real situation. This project is funded by Metropolitan Electricity Authority or MEA. We install charger at the MEA headquarters in Chitlom. These chargers are in service for public and MEA-owned electric car. The trial has been done for more than 4 years and is still providing service as intended. Thank you very much.
Thank you very much for your presentations. So, any audience has some questions to others, to the others? Okay, if you know, I would like to ask some questions. So this is quite interesting also, and which is applied in the real system for the charging stations. So have you the first is is this your method can be applied in other charging stations such as in the PTT station or something like this? You apply only in MEA stations, right? So can you comment about this?
This method is standard.
Okay, it's standard. It can be applied to any stations. Also,
can apply anywhere.
Okay. Also, can you discuss about the figure 10 is what is the control board of the EVS SE? So in this board, it's quite interesting that how much the cost is look like. The cost for this control board. Can you give us some comment?
Control board is about 5,000 baht.
It's not smart. It's very good. Okay, so Now, so in your future plan, do you have any plan to do about this research or improve to be better or apply to other infrastructures? So if you have other plan to do, so please give us some comments so we can follow up your
Next
research more.
presenter will show you some the algorithm.
Okay. Okay, so this is all of my comments. So if the audience has more comments, so please ask the others. Now it looks like no comments. So thank you very much for your work. So we move to the next presenters. That is the transformer load monitoring and EV charging control functions from Mrs. Pachamaipon from the King Mongkut University of Technology, North Bangkok. Same. So
Good morning, Chairman and the conference participants. It is my great pleasure to present my research results to you today. My work is about controlling the electric vehicle AC chargers that connected to the distribution transformers. My name is Pachimapon Gulasingh. I am from King Mongkut University of Technology, North Bangkok. This research is funded by Metropolitan Electricity Authority or MEA. The experiment I show you today has been conducted in the real distribution network. I divided my presentation into 5 parts. I will talk about the motivation of the research in the introduction. Then I will explain the function of transformer load monitoring or TLM in the second part. In the third part, I will show you how to control EV charger with the TLM. Then I will present the result from the real-world experiments. And I end the presentation with conclusion. I will start with some general information on distribution transformer. Distribution transformer is an equipment which reduces the medium voltage. In our case, 24 kV down to 220 volt before feeding to the end customers. Our metropolitan network has been running perfectly for a long time and is still capable of supplying customer demands if there was no electric vehicles. It has been 5 years that the demand of electric vehicles rises. Many house owners have bought electric cars and start to charge their cars at home. One EV can consume current like one small house. If most of the houses install EV chargers, that means you have more than double of distribution transformer load. So what is going to happen? The distribution transformer will overload. This can cause transformer overheated and damage distribution network. At the end, it will affect the reliability of the system. To solve this problem, we can either expand more cable and add more transformers, or try to limit the EV charging to appropriate levels. To upgrade infrastructure to accommodate the increasing EV chargers is a big deal, using a lot of money. In developing countries like Thailand, we can do it in a smarter way. My research proposed the way to delay the upgrade by installing TLM that can control the chargers. Let me introduce you to our transformer load monitoring or TLM. In our laboratory at KMUTNB, we have been designing and making TLM together with MEA for more than 7 years. TLM is an electronic device which measures electrical parameters of the distribution transformers and sends all the data to server. We found that if you use TLM to monitor the transformer, it is just like an electronic energy meter. MEA TLM is smarter. Not only it can monitor the transformer, TLM has control and communication functions far beyond normal smart meter. We can say that it's a real smart grid application or built by Thai. EV charging control feature is one of many applications TLM can do. But today, our focus is only the EV charging control function. I will tell you how this feature works. Let's imagine we have a distribution transformer and a TLM at an electric pole. The TLM will capture electrical data from the transformer, calculate and send command to EV charger. The communication between the TLM and the charger uses Zigbee chipsets. Zigbee is a kind of wireless communication hardware and protocol. This is EV charger we've used to test the scenario. It's a single phase 230 volts. The charging current is ranged from 6 to 32 ampere. The pictures show the front view. The rear view of the charger was open to show a Zigbee communication module. Charger can communicate with EV car via PWM in control pilot wire. The charging will begin when the PWM voltage drops to 6 volts. During the charge, we can change the charging current from the duty cycle of the PWM. According to IEC standard 61851, EV charger between 6 to 51 amp can use this formula to adapt PWM by design current. Duty cycle equal current in amp over 0.6%. So the charger can change current anytime respond to TLM command. Look at this picture again before everything starts. TLM must know transformer limit in kilovolt amp. Then EV charger must sending information about maximum charging current and the connected phase to the TLM. When transformer is overloaded, the TLM will send command reduce current to EV charger. EV charger respond with reduce 10% of current. If 10 minutes pass, it's still overloading. TLM will send command again and charger will reduce current 20% from beginning. If the transformer is back to normal load, TLM will send command increasing current to EV charger and EV charger respond with increased 10% of current. Or if there are small load or enough load left for all EV charger, TLM will send command to maximum current. EV charger will change PWM to full spec 32 ampere. This is from the simulation of 3 EV chargers without TLM's controlling. Transformer was overloaded during 19 to 21 o'clock. In the case of operation with TLM's control, the lower charging current requests were sent at 19 and 20. When the load was low, the increasing current request was done at 21. The result shows that transformer load rapidly increased from 43.3% to 50%. We've on-site experiment with EV charger by manual sending command message from TLM to EV charger. We've found that EV charger can respond to the command and change duty cycle of PWM as shown in the picture. PWM have changed from 30 ampere to 7 ampere. These are pictures from the real-world experiment with real data. The blue line is a normal load of transformer from 5 a.m. to 6 p.m. on December 23, 2019. We have charged 2 EV cars to the system. New load is in red line. You will see that during 11 to 12, the transformer was overloaded. But after 12, we used EV charging control function. The load was down and under limit line. That means no more overload. Both TOM and EV chargers work correctly. After all the experiments, we can conclude that EV charging control function can protect distribution transformer from overloading, which can help to delay the upgrade infrastructure. TOM can control EV charger, and EV charger also can control the current. They work well together. And that's all for me today. Thank you for your attention.
Thank you very much for the presentations. So anyone has comments to these authors?
I would like to ask a question.
Yes, sir, please.
What is the advantages of using Zigbee? Because as far as I know, EV charger maybe support the OCPP protocol for controlling the device via the network.
So the comment give to the authors, what is the advantage of using the Zigbee?
Yeah.
We use Zigbee to communicate between transformer and EV charger. So OCPP we use like OCPP is command from the server to EV charger, but this experiment we command from TLM to EV charger directly by Zigbee.
Okay, thank you very much.
Also, any other equipment that can replace the Zigbee? Do you have any comments about this? If and
Yes.
maybe.
But anyway, by communication, we can use anything.
Okay. So also any comments to the others? The audience can ask. So if not, I would like to ask also in the figure 6, how many profile data that you test? So maybe the profile based on each region, each season is different or not? Can you give like in summer, in winters, or in rainy? Is there different daily profile test, or how many data that you use?
The transformer is the experiment was at the MEA headquarters.
Okay, so this data is provided by the MEAs.
Yes. We work together with MEA.
Okay. Also the figures 13. Also, this is your simulation which use the real data from the MEA.
Yes. The profile is constant, not vary too much with season.
Okay. So how about the cost of this device look like for the figure 2? Can you give us some comment about the cost that you built it? Maybe it will be useful for the audience.
About 15,000 baht.
15,000. Okay. So any audience has some comments? So if not, I will close the sessions. I will close I end this presentations. No. Okay. Thank you very much for your research. It's interesting and apply in real system. Thank you.
Thank you.
So the next presentation, I will move on to the EV conversion performance analysis and sizing of traction motors and battery from driving cycles from Thammasat University.
Hello everyone. Today we are going to present about EV conversion performance analysis and sizing of traction motor and battery from driving cycle. Our group members are Chinawat Tianthapita and Cherathorn Dungthongsup.
I divide the topic into 5 main points. First, problem important. Second, objective. Third is methodology. The next is results. And the last one is conclusion. Okay, let's go to the first topic. This is problem important. The first problem is that the electric car in Thailand are very expensive compared to some countries. From the survey and information, electric cars in Thailand are the second most expensive in the world. Second problem is regarding the carbon emission of combustion engine vehicles. In the past year, carbon emission released 56.3 million tons or 25% of Thailand carbon emission. The third problem is there are highly annual maintenance costs such as oil change or problem with the engine. Objective. First, changing the use of combustion engines to electric cars. Electric cars save money on fuel and maintenance costs because electricity is used instead of oil. Electric cars are not required to do frequent maintenance of the car. And since there is no engine combustion, there is no air pollution that creates global warming. Car exhaust will disappear. Second, analyze the driving cycle to determine the optimal battery and motor size to reduce the use of excess batteries and motor, thus saving the budget. Methodology. In this process and method section, we divide the workflow into 6 steps as follows. The first is driving cycle analysis. At the first step, we use the driving cycle analysis to analyze the travel path to determine the optimal usage. The image above is the routes we use in the test. We divide it into 4 routes from the test and corrected the data correcting to the routes and operating information table. In the second step, research vehicle architecture. We analyze the energy consumption of the path we take on the daily basis of optimize the benefits. The third step, electric vehicle modeling and design. Optimize the car in terms of interior, air resistance, and load slope. Electric vehicle modeling and design. After collecting the speed data of each route, vehicle is then used to calculate the traction force, and after that, the traction force is obtained to find the power. The traction force equation combined with their 4 equations that we accrue from the analyzed vehicle models. From the parameter in the equation is RA denotes the aerodynamic resistance, RR denotes the rolling resistance, RCL is gate resistance, and RF denotes the interior resistance. And another variable is V is velocity, CD is the coefficient of drag, rho is the air density, A is the photon area of the vehicle, and the final block is finding power using the power force and velocity relationship.
The fifth step is battery sizing. We calculate the daily power consumption and analyze it to determine the appropriate size of the battery used in a day. The preceding section traction energy consumption rate and minimum needed power were utilized as the primary factor for designing the battery. The battery minimum necessary capacity is determined by daily power used, charging method, and feeder design. The equation was used to compute the operation distance per day of the time spent approached by the following equation. First, find the energy used by the EV main component and auxiliary equation system. Then find total energy used and distance traveled per day. Then combine them to find energy consumption needed. The variable in this step is EC, is energy used by the EV main component and auxiliary system. PC is load of EV main component. T total is sample duration of driving cycle. E total is total energy used in driving cycle and auxiliary system. ED is the energy used during a driving cycle. D is the distance traveled during the sample driving cycle. D total is the total distance traveled per day. N is the number of driving cycle per day. The average is average distance traveled per cycle, and then combine it all to find E required, which that is the energy consumption needed for battery sizing. Finally, compare the result by bringing together the previous 5 steps and analyzing the best fit for each person or trip. We have an EV conversion design with defining driving cycle data. The design result of this study show that modified vehicle will increase their body weight by 11.5%, but they can travel up to 31.1% longer distance. Conclusion: the IPM motor or interior permanent magnet motor is suitable for the required motor having a high performance at low torque region and medium rotation speed. For battery selection, the maximum energy consumption per day is 192 kWh. The required battery capacity should cover the maximum energy consumption per day. The design specification of the vehicle, the chosen motor and chosen battery. As a result of the modification to the electric vehicle, the total weight has become 10,031 kilo, 11.5 increase from 9,000 kilo. Using a motor with a peak torque of 2,355 Nm and a continuous torque of 990 Nm. The battery capacity is 196 kWh using 2 battery packs placed side by side, weighing 1,120 kg. However, the total travel distance per day can be improved from 94.5 kg to 124.8 kg, or can be called is as a percentage, 32.1% increase per day. Thank you for your attention. If you have any question, you can ask us after this video presentation.
Okay, so thank you very much for the presentations. So audience has some question to the others, you can ask from now. So if no questions, I would like to ask some questions. So this is also interesting work. So it is a big bus, so it's use big batteries capacity. So in my question is how long for the one for charging time for finish the batteries capacity? Can you give us the perspective?
We didn't analyze about the how long to charge the battery, but we calculate about the energy consumption that we use the whole day. Then I think it's not necessary to find that how long you will charge, because you have to just charge once per day
Okay.
when it's dark and yes.
So you usually you charge the batteries when you you operate for 1 day and you charge in the night time.
Yes.
Something like this. So and also the battery you use since it's quite big, how much the cost of these batteries? Can you know the cost of these batteries?
To be exact, is a high price, but I don't want to mention it's very high, but I think
Okay.
it's very long term. We calculate the efficiency about the old engine design and this design. We calculate and we find out that in the long term it's very efficiency more than the old design.
Okay. So you mentioned about long term. How about the lifetime of batteries of this? Can you give give us some knowledge about the lifetime of these batteries that you expect?
About the lifetime, it will decrease efficiency of the battery, right?
Yes.
And how about the result that we have improved the distance? I think the decrease of efficiency of battery is more than it required for the long time.
Okay. So also in the figure 4 that I see you consider have you considered the obstacle of the obstacle or influence of the uphill, right? You consider in your design.
Yes.
The road normally it will be uphill and downhill or something like this. Have you considered this influence in your design, or you just consider it as the flat?
We neglect.
Flat road.
We only consider in the flat road.
In the flat road. Okay. Okay. Thank you very much for your presentation. Finally, so if audience have some comments, please give to the authors. So if not, I would like to close this sessions. So thank you very much for your time today and your participations. So the session is end from now. Thank you very much.
Thank you, Professor Thongchat, for joining us.
Thank you very much, sir.
ครับ ยกมือมีปัญหาอะไรทางเทคนิคหรือเปล่าครับได้ยินปกติครับอาจารย์ครับโอเค
ระหว่างรอเซสชันสตาร์ทผมขออนุญาตเช็คเปเปอร์นะครับ during waiting for the session to start may I check the presenter in this session if they are ready or not is the presenter of the first paper here the first paper should be implementation of harmonic compensation by Subharak and Sakda is the presenter here okay if you can for the presenter and for the audience you can unmute your microphone and ask the question or speak out loud in case you have any issue presenter the first paper not yet the second paper 4015 by Mohammad Haram and co effect of the parasitic resistance is the presenter of this paper here yet all right please answer me if you are in the conference room already all right okay not yet right the third paper we haven't got your video presentation yet but I just curious if the presenter of the paper of performance of single phase Vienna rectifier is already in this room.
Yeah, already.
Okay, so I haven't got your video presentation, so I suppose that you're gonna present in the session, right?
Yes.
Okay, so in that case, you need to share your screen. You may want to test your
Yes,
presentation
I want to test
file
it.
at this moment. Okay, you can try. All right. So, any issue?
It's not sure.
All right. You can share the entire screen or select to share the presentation file. You have to choose the correct window to be sharing.
Okay, just a moment.
Okay.
Uh,
So, and in that case, I will move your presentation to the last time slot. All right.
see it? You see my presentation?
Okay, can you enlarge?
Already last.
Can you make it full presentation mode, full screen presentation mode?
This one?
Yes.
You see it, right?
No.
Okay.
You have to set the sharing screen to this one.
Sharing screen.
I think you choose only the PowerPoint, the main PowerPoint window, not the presentation window.
Presentation. I'm already in the presentation.
No, I mean your option in sharing to WebEx.
Option sharing. Where is it?
Okay, never mind. In that case, if there is any difficulty, I accept this slide. Okay. You can use the you can make a presentation using this window. All right.
Yeah.
Yeah. Can you move to the next slide?
Just a moment. You see it?
Yes. Okay. All right. So another one, please. Move until the end of the slide.
Already in.
No. Can you unshare your screen and share again, please?
Okay. Unshare.
Actually, we require the presenter to do the video recording to prevent any difficulty.
See it?
All right. So just move to another slide. Yeah. Okay. This should be okay. All right. So you can unshare your screen.
Okay.
And please be aware that the time limit is 12 minutes. So please keep your presentation in time.
Okay.
Right. So the next paper, ripple capacitor voltage analysis, is the presenter here yet?
Yes. In fact,
can you turn on your
hello?
All
You
right.
hear me?
Yes.
I'm Metipot.
The presenter of ripple capacitor voltage analysis, right?
Yes, in fact, I have two papers.
All
The
right.
first one is
The second one too.
yes.
Okay, so you're gonna present both paper, right?
In fact, it's my colleague in Iran, but I think they have difficulties to join us because the sanction of WebEx. But nonetheless, I will.
All right. So anyway, you are the co-author of the paper, right?
Yes, of course.
Okay.
Thank you.
Maybe you can answer the question for
Yes.
in this case. So okay, and the last paper, design and construction circuit drive system.
อาจารย์
อาจารย์ชานรงค์อาจารย์ชานรงค์ Okay. อาจารย์ gonna present it by yourself, right?
Yes.
Alright. Okay. Welcome to the session then. Okay, because some of the first paper, I haven't got any response from the presenter of the first paper, implementation of harmonic compensation. I think the author Suparat, I see the ID in this room, but
I am here.
all right. Okay, the presenter. Yeah, so you're gonna present for the first one. Okay, the session will start at 1 p.m. So you have time to prepare. Anyway, for the second one, Mr. Metipot, right? For the third one, Mr. Boripat. Metipot. So I think every presenter are in this room now. So I will just explain a little bit about the presentation, right? I will start the session by introducing the presenter, or if you send us the biography in advance, or if not, I may ask you to introduce yourself for a little bit, and then the video recording will be played. And after that will be 3-minute Q&A session. So during the presentation, I may ask the presenter to turn on the camera, but turn off the microphone. And in Q&A session, if the audience have any questions, you can turn on the microphone to ask the question directly to the presenter. If there are any difficulty, you can put your question in the chat box. If time allow, I will ask that question to the presenter. So may I ask the admin staff, is the video playback for the first presenter ready?
Yeah, it is. But Professor, for the first video, it's almost 14 minutes. Do you want me to play it to the end or stop at 12 minutes?
Okay, that's fine. Okay. สัมภาษณ์อาจารย์ณัฐพัฒน์ จะสบาย So I think the session is ready. Is the staff ready? Is the recording on? Not yet. Just wait a bit. May I introduce myself first? Good afternoon, everybody. Welcome to ECTI in the afternoon session. This session will be power electronics session. There will be 5 papers to be presented, and I think it will be very interesting topic to discuss. So hope that everybody will join us at the Q&A session. Okay, the first paper will be implementation of harmonic compensation for 3-phase grid-connected voltage source converter under grid voltage distortion. The presenter will be Mr. Suparak. If I pronounce your name incorrectly, please apologize.
Yes, correct.
Yeah. He received the master degree of electrical engineering from Chiang Mai University, where he is currently working toward the PhD degree in the area of smart grid technology, School of Renewable Energy and Smart Grid Technology at Naresuan University, Thailand. Okay, and now he has been with the Department of Electrical Engineering, Faculty of Engineering, Rachamankala, University of Technology, Lana. Okay, his research interests include switching power converter, grid-connected converters, electrical machine and drive, and power quality problems. So I think the video is ready. So the presentation can begin now.
Good afternoon, Chairman and everyone in this section. My name's Suparak Sita. I am PhD student in Smart Grid Technology at School of Renewable Energy, Naresuan University, and also I am lecturer in Rajamangala University of Technology, Lana. Today, I am going to present part of my research. My research topic is implementation of harmonic compensation for 3-phase grid-connected voltage source converter under grid voltage distortion. This is content of my presentation.
Nowadays, more and more converters are used in the daily life. It is contained in many electrical equipment that are controlled by inverters such as air conditioning, washing machine, water pump, also LED lamp, television, and the computer. This electrical equipment make the current distortion to the grid. It is the pollution in the electrical system. In this slide show the low voltage power grid system, which consists of the distributed transformer connect between medium volt and low volt side. The nonlinear load are connected in the point of the common coupling, or PCC, which inject the harmonic current into the grid. Therefore, if the low voltage power grid system has high harmonic current, it will affect the voltage, resulting in the high distortion. This effect will be more intense if the position of the nonlinear load is very far from the distributed transformer due to the high grid impedance. The grid-connected voltage source converter will use for bidirectional power flow between AC side and DC side. The EV charging station is the one example of the voltage source application. In the future, there will be an enormous amount of electricity consumed due to the EV want to consume the electricity from the grid. If there are many grid-connected voltage source converters in this system, it will make the grid unstable, which case of the weak grid condition. Not just a problem with electricity consumption only. In the present grid system, there is still connected to the energy source from clean energy such as solar cell, wind turbine, and sometimes the battery is the source of the system. On the right-hand side of this slide, show the harmonic voltage distortion caused by the nonlinear loads inject harmonic current into the grid. The voltage source converter without harmonic compensation will create a high-order harmonic current when connected to the grid voltage distortion. It is in the figure waveform that the grid current IG is artificially distorted by grid voltage harmonics. On the left-hand side, show diagram of the three-phase grid-connected voltage source converter with a harmonic compensation of the current control loop, which is structure used in this research. This paper focused development methodology of a three-phase grid-connected voltage source converter with the proportional integral path multi-resonance controller or PIMR controller in the synchronous reference frame for mitigation of grid voltage harmonic as shown in the figure. Also, this paper expands the design current control of the voltage source converter and its discrete time control scheme. The control scheme can be directly transferred to discrete time control system implemented on DSP controller. The proposed method was validated with a hardware in the loop or HIL real-time simulator and demonstrate hardware of 5 kW three-phase grid-connected voltage source converter with an LCL filter. This slide, I will describe the basic concept of the multiple harmonic compensator. On the right-hand side show the proposed control scheme. In blue dash box show the DQ frame current control, which is used to control the DQ frame current IGD and IGQ. The proportional integral controller GPI regulates the DC quantity caused by the transformation of the fundamental component current into the DQ frame. The multi-resonance controller regulates the AC quantity of both negative and positive sequence component in the DQ frame, which is used to eliminate harmonic current caused by the distorted grid voltage. The PIMR transfer function in the continuous domain is given by equation 1. Consider equation 1 only for generalized resonance controller GRS as shown in the equation 2, where KRS is the resonance gain in each harmonic compensator, omega n is the normal grid frequency, and H is grid voltage harmonic order in synchronous reference frame. Result from the harmonic order in the stationary frame, which become the determinant of the DQ frame current control loop. The resonance controller transfer function of equation 2 is constructed from double integrator configuration shown in the left-hand side figure. To activate the current control loop on DQ frame, the PI controller for the fundamental component current is designed according to design methodology in reference 8. The PI controller gain can be obtained from equation 3, equation 4, and equation 5. For the resonance controller gain, for example, in order 6 and order 12 are added to eliminate the voltage harmonic, order 5, order 7, order 11, and order 13. For my work, the resonance gain are set at KR6 equal KR12 equal KI in the fundamental loop divided by 3. To confirm the stability of the current controller, the open loop transfer function in the continuous domain of the voltage source converter with the LCR filter can be written as equation 6, and the perfect transfer function of the LCR filter is given by equation 7. I am used the parameter of the table 1 to calculate the parameter gain of the current loop. From equation 6 can be created the Bode diagram. We show the frequency response of the simplified open loop transfer function with the PI controller and PIMR controller. The target phase margin is set at 60 degrees. For the PI controller, the DC loop gain of 100 dB is large enough to track the reference current with a zero steady state error, but not enough to mitigate the current harmonics. For the PIMR controller, the DC loop gain and the loop gain at harmonic order 6 and order 12 are greater than 100 dB. Meanwhile, the phase margin of the PIMR controller is 48 degrees, which is still large enough to guarantee the control stability. To transform the resonance controller in continuous time domain corresponding at figure 2 to the discrete time domain, the forward Euler method and the backward Euler method are used for the forward and feedback indicator. Therefore, the controller scheme of the multi-resonance controller at the harmonic order 6 and order 12 can be rewritten in the discrete time domain according to the figure on the slide, and the discrete time domain transfer function of the resonance controller can be expressed as equation 8. For programming of the multi-resonance controller, each harmonic compensator is converted to sample pseudocode as described in figure 5. This code is executed each sampling time period by simulation software or digital signal processor. The proposed control technique was modified through simulation in the MATLAB Simulink, hardware in the loop implementation, and hardware implementation. On this slide show experiments of the voltage source converter was modeled in the Oppo RT OP4510 real-time simulator. The power circuit of the voltage source converter was implemented on the FPGA base via EHH tune block in the MATLAB Simulink with a time step 220 nanoseconds. The current control scheme was implemented on the Texas Instrument TMS320F2A379D. The grid voltage, grid current, and DC bus voltage was scaled down to connect to DSP, and the grid signal from DSP was sent back to the hardware in the loop system. The simulated signal were measured by an oscilloscope via analog output of hardware in the loop system. On the right-hand side, show the laboratory hardware implementation. The voltage source converter was connected to the coma regenerative grid simulator, which provides the three-phase distorted grid voltage according in the table 2 and changing the frequency. The DC side of the voltage source converter was said to be a 700 volt constant voltage by the coma DC power supply. A 5 kW LCR filter 2-level voltage source converter was used in the hardware prototype. The voltage source converter was controlled by the same DSP used for hardware in the loop with the same voltage and current sensor gain. And next, on this slide show the dynamic response of the voltage source converter when the reference current changes abruptly. Initially,
Both reference current was set to 0, and then reference current was suddenly changed. IGD reference equal minus 0.7 per unit, and IGQ reference equal 0 per unit. The experimental results show that the of the gate current waveform can be changed in accordance with the reference current.
วาง
The
สาย
gate
แล้ว
current and
โทร
the
อะไรบ่อย
steady-state condition are close to sinusoidal waveform. The simulation results and the experimental result of the hardware in the loop and hardware implementation are in close agreement. Moreover, the proposed harmonic compensator can mitigate the effect of the frequency variation with and without distorted gate voltage. On this slide show the performance of the current loop when changing grid frequency without distorted grid voltage. The grid frequency changed from 47 Hz to 50 Hz and 52 Hz respectively. The grid voltage background has very low total harmonic distortion. So, the grid current with the PIMR controller at the all frequency change is lower than 1%. On the right-hand side waveform, the grid voltage is still distorted. At the bottom waveform, the harmonic compensator without frequency adaptation cannot mitigate the effect of distorted grid voltage when the frequency changes from the normal value. The THD of the grid current is greater than 5% at the grid frequency abnormal, which exceeds IEEE 1547 standard. On the other hand, the harmonic compensator with frequency adaptation still maintain low THDI value at the frequency out of normal value. The grid current had THDI approximately 1% that comply with IEEE 1547 standard. The experimental results for the hardware in the loop are very close to those of the hardware implementation. Conclusion: this paper proposes implementation methodology for current harmonic compensation scheme of three-phase grid-connected voltage source converter under voltage distortion. The PIMR controller was used for the voltage source converter current control loop with frequency adaptation capability. The multi-resonant controller will expand in the discrete time domain and experimented in the distant platform. The experimental verification was described the hardware in the loop and hardware set up under the distorted grid voltage. The simulation and experimental results of the proposed system achieve mitigation of the effect of distorted grid voltage under the frequency variation. The grid current with the proposed control system comply with the IEEE 1547 standard. Thank you for your attention.
Okay, thank you very much for the presentation. I think the work is very interesting. So if the audience have any question, we have maybe 2 minutes for the Q&A. Okay, during waiting for the question, can you explain a little bit more the reason why PIMR is chosen for this application? What is the advantage over the other controller?
Okay, you can hear me? Hello.
Can you volume up a little bit?
Okay.
Yeah. Please. Do you hear the question?
Yeah, I hear.
Okay, we can hear you too. So I just can you explain a little bit more why PIMR is chosen for this application?
I think that this controller is very easy to implement it. The PMI is general. I think everybody know PI controller, and the resonant controller is I think it's very simple for implemented in the AC component control. I think the two controller is when passed together, I think it's very easy to implement it. Yeah.
It's because of the simplicity of the
Yeah.
implementation, right?
Yeah.
So how about the stability? Is it enough?
Yeah, I think I think it's enough. And when I put the PR controller in the system, the stability is drop to drop a little bit, about 48 phase phase margin 48 degree. Yeah, I design I set to design it 60 degree. Yeah.
All right. Okay, so it's still within the range of acceptable stability, right?
Yeah.
Okay. Thank you very much. So then I will move on to another presentation. The second presentation will be effect of the parasitic resistances on the voltage gain in a DC-DC modular system. I'm not sure if the presenter is here yet, Mr. Metipot, right?
Sorry, yes, I am here, but the presenter, Mr. Perham, is here also.
Also, all right. So
Oh,
then I will introduce the presenter a little bit. Yeah, Mr. Param, is that right?
Yes, hello.
Param, are you here yet?
Yes, I'm here.
Okay, well, welcome to the conference.
Thank you.
Mr. Param graduated with a BS degree in biomedical engineering from the Islamic Azaz University of Nakhafabat and Shahid Beheshti University with a master degree in Iran. So his research interests include renewable energy, power electronic interfacing system, and education. So I think we are ready to watch the presentation. We may start the presentation now.
Hello, everyone. First of all, let me thank you for coming here today and the organizers of this meeting for inviting me here. Let me start by saying just a few words about my own background. My name is Parham Karimi and I graduated from Shahid Beheshti University with a master's degree. In addition, I have some background in biomedical engineering field. What I'd like to present to you today is effect of the parasitic resistances on the voltage gain in a DC-DC modular system. In this article, the behavior of two-module converter with a parasitic resistance is investigated. MATLAB Simulink software is used to perform the modeling, and the voltage gain and the duty cycle of DC-DC converter are studied. This presentation is structured as follows. I start with a brief introduction about converters and voltage gain. After that, we talk about the system, its state equations, and hypotheses. Next, we introduce two scenarios for parasitic resistances. Finally, simulation and theoretical results of the proposed system is presented. And at the end, we will have the conclusion. The introduction is the first part that we talk about. PV panels are one of the powerful devices that generate electrical power among renewable energy systems. PV systems are affected by shading, relative differences in the orientation, panel's temperature, dust, and spot dirtiness, such as leaves or bird dropping. This issue can generate mismatching in the power generation of the panels. The fuel cell has received a great deal of attention as a non-polluting generator of electricity. However, fuel cells have some serious problems. Fuel cell problems are summarized in this slide. During using of fuel cell system, some heterogeneity between the cells constituting the stack can occur. The voltage of one specific cell in the stack may decrease due to particular aging or local malfunctioning, such as drying. Consequently, extra heat is produced in this cell, leading to an increase in its temperature and adding voltage loss. The snowball effect can cause the failure of the cell. Hence, by applying energy management to each cell, a lifetime of fuel cell stack can be enlarged. Converters are evolving rapidly nowadays. They have a wide range of application in renewable energy field, such as wind farms, fuel cells, and photovoltaic panels. As we've said, these applications have some challenges like the snowball effect in the fuel cell and mismatching in the photovoltaic panel. These problems can be solved by converter. Based on the converter's need and applications, criteria are needed to compare these converters. Voltage gain, ripple, efficiency, and stress on the elements are criteria that can compare these converters with their help. Voltage gain is one of the most important parameters in selecting converters. The output voltage ratio divided by input voltage ratio is called the voltage gain. One of the solutions for reaching high voltage gain is the series topology of the boost converter. Some of the isolate topology that use transformers or Coope's inductors are used to provide high voltage. However, this topology are suffered from high losses, large dimension of the converter, and high weight. Some converters can work without transformers and have a favorable specifications. Three-level converter are one of the alternative converters. Now we start to introduce a studied system. As we said, three-level boost converters are alternative for classic boost converters. In this article, a modular converter is considered. The studied system is shown in figure. The modular converter topology consists of the two three-level boost converters. We have a three capacitor that shows with C1, C2, and C3. The capacitor C2 is common to both converters. L1 and L2 are two inductors in the system. R1 and R2 are considered as the inductors resistances in this article. RSH is the load resistance. The equation of the system in normal cases are presented in the table. The state variables are the current of inductors L1 and L2, and the voltage of capacitors C1, C2, and C3. So the system has 5 state equations. Theoretical calculation. As you can see here, we have a several hypotheses in this system. Input voltage are equal to Vi, capacitor voltage are equal to Vc, inductor's resistance is represented by RL, D12 and D21 are equal to DC. In addition, D11 and D22 are equal to D as a duty cycle. Recalculating the equations with a hypothesis leads us to the voltage gain equation. N in these equations represents the number of modules in the modular boost converter. The answer between 0 and 1 is acceptable at the extreme point of voltage gain equation. For this reason, we consider only one condition. In this section, the simulation results and theoretical results are presented. Two cases are considered for parasitic resistance. In case 1, nominal load resistance is considered. In case 2, half of its nominal value is considered. The simulation results are presented in this slide. During step time t is equal to 0.04 seconds, the resistance value changed from the nominal value to half of it. The value of 4.51 and 3.241 are the voltage gain in these two cases, and the duty cycle value are 0.61, 0.80 for the first case, and the 0.46 and 0.73 for the second case. As you can see in the theoretical result, show a voltage gain of the 4.51 for the duty cycle of the 0.8 and 0.6, the exactly same as the simulation result. In case 2, voltage gain equals 3.24 at the duty cycle of the 0.46 and 0.73. And finally, the conclusion part. In this paper, the effect of the parasitic resistances of the inductors for a modular converter is examined. Using the system equations of the converter under study, including changes in inductor current and capacitor voltage, and the voltage gain is obtained. Then, extreme points of the voltage gain are calculated. Using these relations obtained from theoretical calculations, the voltage gain waveform are plotted based on the changes of two duty cycles and compared with the simulation results. I'll briefly summarize the main issues. We considered parasitical resistance in two cases. Case 1, load resistance is equal to the nominal load resistance. Case 2, load resistance is equal to half of its nominal value. As you can see in the table, both theoretical and simulation results show similar numbers. As a result, the resistance of the series of inductors affects the scope of the duty cycle, and the number of the modules care must be taken in their selection in particular cases. This paper results from the collaboration between Iran, Thailand, and France, and it's my honor that my colleagues give me a chance to present their efforts here. Thank you for your attention.
Okay, thank you very much. Okay, the work seems to be on simulation side. Okay, so is there any question from the audience? If you are not comfortable in using microphone, you can put your question in a chat box. Any question? So then I may ask just some question. How do you obtain the parasitic resistance value to put in your simulation? Do you measure or do you just estimate?
Okay, thank you for your question. In this paper, we consider parasitic resistance and we calculate the voltage gain and duty cycle in two operation points by changing the load resistances. The parasitic resistance is the inductor's resistance, and we consider constant value.
Yeah, and how do you get that value? What is the value anyway for your parasitic resistance?
I think it's and this a specific question. I think Dr. Galaxos can answer better this question.
So sorry, I am Metipot. I am the co-author.
All right. So
Yes, that's fine.
I can answer this. In fact, I measure, in fact, the DC resistance of the inductance.
All right.
Just only DC inductance. And
okay, so the
the
inductance
value, in fact,
resistance
because
value.
the laboratory, the experiments will be done in Thailand. And the party of simulation we done in France and Iran. Thank you.
Okay, thank you. Because I think parasitic resistance is quite common in power electronics, and it's quite an issue. So to get that, to quantify the parasitic resistance value to include in the simulation will be quite helpful to foresee the issue that may occur. So thank you very much for the presentation. I will move on to the next presentation. Okay, the next presentation will be performance of single-phase Vienna rectifier in an induction heating application by Mr. Baripat. So since the presenter did not prepare the video presentation, so I will ask the admin to grant the authority to share the screen to the presenter.
Okay.
Okay, please proceed. And the time limit is 12 minutes. Thank you.
You see it? Did you see the presentation?
Not yet. Please share your screen.
Oh, okay. I'll share it.
Okay. Okay.
You see it? Did you see my screen? Hello?
Yes. Yes.
Okay. My name is Bodipat. I'm studying in the Rashomangala Institute.
Maximize your slide.
Sorry?
Maximize your slide.
Oh. Already?
Yeah, it's okay because we have tested and there seems to be a problem with full screen mode. Okay, please.
Okay. So okay, next one. I coming here for present the presentation for the performance of single phase Vienna rectifier and induction heat application. First of all, this presentation I got the requirement from industry for for make the induction heat, but the induction heat that got the harmonic for the output is too many, so they want to reduce the harmonic output like minimum like 0.85 or 0.1. That's why, and the I have to make this induction heating with the low harmonic. So first of all, I have to introduce to my basic induction heat. First, the first part of induction heat is in the input that we call front end, and then it move to the filter and inverter and the load. So this presentation will point to the front end because this make the harmonic. But the front end is rectify the power waveform like this presentation. The current waveform is not in phase with the
The slide
voltage.
did not change.
Sorry. Sorry. Change already?
The slide not change. Change slide.
Sorry, could you please share the screen again?
Okay.
Okay. That's fine now.
Okay. The rectifier have the output, have the input waveform not in phase. The current in the red color is not in phase with the voltage. The power factor input is 0.85, 0.75. Then the harmonic THT harmonic is 0.4, 0.05, 0.08, and that's why I have to find the circuit that make this better. The circuit that this is I select based on the control system is choose have one switch for easy to control it. That's why I choose the Vienna rectifier. This is the circuit, the Vienna rectifier. Have the C part also, have the front end, filter, inverter, and load. The Vienna rectifier, the point of this current the circuit is the switch S1 is the P channel in P channel MOSFET, not N channel. Because if you use N channel, is circuit it work not properly. The control of this circuit is the current control. It come is the one switch from the circuit below in the lower here. The L and C of input, L1 and C1 of input here is use conform the circuit is the question on the right side. Is the part of the circuit when current in positive and negative. In positive in the left side and right side in the negative. And then we come to inverter side. Which side is the normal one? Is basic in the inverter circuit. Is it switch is on opposite, like Q1 and Q4 on the same time, and Q3 and Q2 is another time. The parameter on simulation in the right side is on the linear file, and left side is in the left side is the linear file, and right side is near the inverter. The circuit for simulation is this one. Result, the input circuit, the input circuit in the left side here is the input circuit. The waveform is a side, and then in the right side, the current will in phase on of the voltage. The waveform and waveform of the output here is the left side is the voltage, and right side here the current. The percentage HD is 0.105. It's minimal than the first one. This is the output of the inverter for the load. The summary of this one is purpose here is the power factor is 0.992, and percent per DI is 10%, and the O1 is 0.75 on the power factor, and percentage DI is 40%. That's its end of presentation.
Okay. Thank you very much for the presentation. So this work shows some improvement at the result. So any question from the audience? I think there may be 1 or 2 questions. We have quite enough time. Okay, so I didn't notice in the presentation. May I ask, what is the switching frequency used for Vienna rectifier?
Oh, okay. Vienna rectifier it uses 15 kilohertz.
15 kilohertz?
Yes.
Okay. And is there any relation between switching frequency and the output ripple? Because I have a look at the output voltage, and it seems that the ripple is quite noticeable. It's quite
the output.
Yeah, the output, the ripple output voltage is quite big. Can you explain a little bit why the ripple is very noticeable?
Okay. The ripple. Ripple because the C1 have the design for the minimal for setting. And if you want to ripple better than this, we increase the C1.
All right, because a smaller C is used, right? So if we use a bigger capacitor, and will it affect your other parameter design?
The C1 is a filter, and the parameter design we use the C input CI, so not affect too much.
All right. So I think we have run out of time. So we may move to the next presentation. Thank you, the presenter.
Okay, thank you.
Okay. The next presentation will be a ripple capacitor voltage analysis on 2-input 3-level boost converter. The presenter may be Mr. Metipot, right? Yeah.
Sorry again, Mr. Chairman. In fact, it's my colleague Muhammad Afkar.
Okay. All right. Sorry.
He's in Iran too, but the how to say the speed of internet in Iran right now is not quite good. So maybe.
All right. So I see there is a difficulty in getting online, right?
Okay.
So,
okay.
all right. In that case, I think there is a biography in the presentation already. So we can start the presentation video.
Hello everyone and welcome to my presentation. First of all, let me thank you for watching this video. My name is Muhammad Afkar and I graduated from Shahid Beheshti University with a master's degree. I am delighted to virtually be here today. As you can see on the screen, our presentation topic is ripple capacitors voltage analysis on 2-input 3-level boost converter. In previous works, we have introduced a modular DC-DC converter based on a 3-level boost converter. In this article, we have studied an output capacitor ripple in this modular converter. Mismatching input power supplying to the converter can be occurred due to an operation condition of the sources. Hence, ripple voltages for the output capacitor linked to such input powers may be different. The converter is controlled using a classic cascade control to ensure that the input current and output voltage at the desired operating are at the desired operating point, and the simulation results obtained by MATLAB Simulink software are given at the end. The presentation is structured as follows. I'll start with a brief introduction about modular DC-DC converter. Then we introduce two module 3-level boost converters and we talk about modulation techniques. And next, the voltage comparison is done in two cases. Then we present simulation results and finally conclusion is presented. So we start with introduction part. In some applications such as fuel cell and photovoltaic systems, output voltage is low and they have problems such as mismatching effect in PV and a snowball effect in fuel cell. To increase voltage and also to manage these limitations, using a separate DC-DC boost converter can be a solution. To increase voltage even more, the voltage capacitors are connected in series to meet the load requirements. In this arrangement, a new problem arises which caused because of difference in power producing of sources and their conditions. If one of the sources produces less power, the output capacitor voltage of its converter decreases, which causes unbalancing voltage problem. The converter which has been proposed in our previous works presented in this slide. It has several merits such as modularity, multi-input connecting capability, and also can solve voltage unbalancing problems. The nonlinear control was presented to balance the capacitor voltages while the input powers could be perfectly controlled. In this paper, an analysis of the output voltage capacitor's ripple is presented. In this section, the studied converter and modulation techniques are presented. The studied system is shown in the left figure. This modular converter topology consists of two 3-level boost converters. Within this arrangement, the capacitor C2 is common to both converters. In the right table, the state equations of the system can be seen. Two methods are used to generate a command signal in the PWM block. These methods are introduced in this slide. In the first method, the triangular signals are the same for the command signals U11, U22, and the signals U12 and U21. In the second method, the triangular signals are the same for the command signals U11 and U21 and the command signals U12 and U22. The steady state voltages of three capacitors is presented in these figures. In the first method, the capacitor voltage waveforms of the first and second modules VC1 and VC3 coincide. The common capacitor VC2 differs in phase with the other voltages. It can also be seen that the amplitude of this voltage is slightly larger than the other two voltages. There is a phase difference between all voltages in the second method. The ripple for first and second capacitor voltages are the same but different from the common capacitor. In the first method, at this point, the common capacitor ripple is more than the others, and in the second method is less. Also, in the first method, the frequency of the common capacitor voltage VC2 is the same as the frequency of the other capacitors, but in the second method, this frequency is doubled. Consequently, we use the second method for the further investigations. In this section, the ripple voltages for the output capacitors is presented. Under the assumption that losses are neglected and the input voltages are constant, there are two cases. P1 is equal to P2 and the second case, P1 is less than P2. Case 1, equally sharing input powers. When the input powers for both modules are equal, the duty cycles D11 is equal to D22 and D21 is equal to D12. The ripple of voltage for C1 and C2 can be obtained. Considering the shown figure, the middle capacitor C2 sees two currents in each switching period. We can find the current flowing through C2 as follows. As it can be seen, if all capacitances are chosen equally, the ripple voltage for the middle capacitor is half of the ripple's voltage across the other capacitors. This confirms the simulation results given in slide number 10. Under the mismatch condition, the input powers for both modules are different. A coefficient alpha is introduced to make the total input power constant, which is PT. It can be generated by a supervised controller. The coefficient alpha is defined as it can be seen on this slide. Under this scenario, we can find current flowing through C2 using D21, and we can get this equation. The ratio of ripple voltage of the capacitor C2 and C1 is given in this slide. In this section, the system simulation, including the converter and the controller, is performed. The value of parameters considered for the simulation are given in this table. The indirect sliding mode control is used to govern the system. Parameters of the controller is given in this below table. Okay, the scenarios for the simulation are given in the figure. After the converter starts to operate with RCH equals to R, then at the time t equals to 0.2 seconds, the load decreases to half. For the first scenario, the coefficient alpha is 1. It means that the two modules produce the same amount of power. Then at t equals to 0.8 seconds, the coefficient alpha is changed from 1 to 0.7. In the figure, the voltages across the output capacitors are presented. There are three parts, part 1, 2, and 3. The first and second parts are under the same conditions, where the input powers for both modules are the same. For the third part, the input powers for both modules are different, according to the coefficient alpha. As it can be seen, the ripple voltages for the first part, the ripple voltages for VC2 is the smallest, while the others are the same. For the second part, where the load resistance is stepped from R to half of R, the ripple voltages increases due to the load increasing. However, it is like the first part. For the third part, the input powers for both modules are different, as the alpha coefficient is chosen to be 0.7. Conclusion. The ripple voltages on output capacitors for a 3-level boost converter with 2 input sources has been presented. Under the situation where the input powers for both modules are identical, the ripple voltages of the common capacitor is half of the ripple's voltage across the other capacitors. When mismatching input power supplying to the converter occurs, the ripple voltages of all capacitors completely change. The ripple for the middle capacitor increases, whereas the others may increase or decrease. The analysis results can be used as guideline for designing the converter under mismatching input power conditions. It was my pleasure to be here today to present this paper that is joint work of Iran, Thailand, and France. And I appreciate my colleagues for giving me the chance to present this article and represent their efforts and investigations. Thank you very much.
Thank you, the presenter. It's unfortunately that the internet speed is not allow him to join us in this session, or is he here yet? Okay, so
yes, Professor, I'm here.
All right, so
Can you hear
welcome
me?
to the conference. Yes, I can hear you clearly.
Thank you so
So
much.
I have a quick question for you. It seems that the common capacitor will have a very unbalanced ripple condition. So when implementation, will this affect the lifetime of this capacitor more than other capacitor?
Of course, the common capacitor has a varied ripple. If you want to compare with other capacitors, but our aim to use the common capacitor is to balance the output voltages of the input our input sources. If they are varied, we have no chance to make the system to balance the output capacitors. So yes, the output capacitor, if the powers are identical, yes, the output, the common capacitor ripple has a varied, a different varied ripple difference to the others, but in the condition that the powers are not the same, that it's the normal condition that we know, the output capacitor ripples are the same.
Thank you. So because it's always a trade-off between a new design, right? Between this and that when we try to implement multi-level converters. So maybe my last question for you. So do you have any idea how to reduce this ripple for all those capacitor in the circuit?
By implementing the first method, we have the same but a little higher ripple by the common capacitor, but if we could choose a larger capacitor for the capacitor, the output capacitors, we can reduce the ripple, as it can be seen on the equation we have in the article, or increasing the frequency.
All right. Thank you, Raj. Thank you for joining us today. Okay, so
thank you so much. I'm glad to be here today.
Yes. Next year, try to be in Thailand, right?
I hope.
Okay. The next presentation will be the last one of our session. It's from Chan Chanarong. The title is Design and Construction Circuit Drive System of Electrode-Less Induction Lamp. So maybe the presenter may introduce a little bit about yourself before we start the video. Is the presenter here?
Yes, I presenter.
Okay, so can you introduce yourself a little bit?
Yes.
Hello.
Hello.
Yes.
Cannot share content.
Yeah, that's okay. I just want you to introduce yourself before we start the video recording. Okay. Can you just tell us a bit? What are you doing? Where is your workplace? Something like that. All right. Maybe we can ask later. Okay. Then I may proceed with the video presentation first, and then we will ask more information at the Q&A session. So should we begin?
Hello everyone. I am Chanarong Noi Bangyang from Ayutthaya Rajabhat University. Today, the research paper will be present on Design and Construction Circuit Die System of Electrode-Less Induction Lamp. Objective of this research: paying attention to power factor correction of induction lamp by focusing on solving power factor with a total of 4 circuits and the diverse circuit can supply power to the lamp as less 40 watt. The control circuit can provide voltage between 180 to 440 voltage. The frequency switch circuit is in the range of 20 to 150 kilohertz as approximate for the device. To produce light, the ballast supply high frequency current to the electric coil. The 4-line magnet on either side of the lamp emit an electromagnetic field which excite the electron inside the lamp. As electron accelerates inside the bulb, they collide with mercury atom and produce ultraviolet UV radiation. The UV light then causes the spectral phosphor coating inside the glass to react in a way that creates fluorescent light within the visible spectrum. This picture lamp comparison. Lumen maintenance curve for wireless commercial lifetime. An induction lamp is an electric bulb without burning of the fragile electrode inside. The lamp life is therefore increased to 100,000 hours, which is more than 500% longer than high intensity discharge and fluorescence. This picture lamp comparison. Induction LED metal halide high pressure sodium lamp. Focus induction lamp. Lamp light. Lighting efficiency CRI. About range more than 80 on the color rendering index with a relative color temperature for luminance maintenance approximately 2,500 to 6,500 Kelvin. A prototype of induction lamp circuit is will consist of key important parts as follows: the rectifier circuit, control circuit, and the resonance rod circuit. The first part generally apply C filter to the load. The result is an electric current in range impulse waveform. Part 2 use a standard field circuit to improve the power factor. The result is electric current is a sine wave and the impulse is reduced. Part T use a field circuit with resistance RT to improve power factor. The result is electric current waveform. It is a sinusoidal waveform with a lower impulse value than the second part. Part 4 using Valley-Field circuit with double and RV. The result is electric circuit. It is a sinusoidal waveform with a lower impulse value than third second and near side waveform. The topology of research, EMI, and filter state. This state will fill large amount of unwanted harmonic generated at the line that interfere with the performance of other electronic load. 2. AC to DC rectified state. This state convert AC to DC voltage using bit circuit and capacitor filter. 3. Power factor correction control state. This state act as power factor correction circuit by 4 Valley-Field type of various method. 4. Resonant inverter and driving state. This state acts as high frequency inverter by using half-bit converter as high frequency, which will be tested to find the proper frequency. And when using all 4 types of circuit to improve the power factor, will be get follow the result of the electrical signal measurement experiment. First, general C filter circuit, no power factor correction. When increase the input voltage more, will make the value of power factor and harmonic value are reduced. 2. Use standard Valley-Field. When increase the input voltage more, will make the value of power factor and harmonic has a lower value than part 2. 3. Valley-Field with RV circuit. When increase the input voltage more, will make the value power factor and harmonic the decrease was greater than part 1 and part 2. 4. Valley-Field with voltage double and RV circuit. The result, when increase the input voltage more, will make the value of power factor and harmonic has greater decrease. Final result is compare power factor increased and total harmonic distortion decrease, create factor and lux illuminant. The graph show the compare of value. Get all 4 graphs. Reference. Question and answer. Thank you very much.
Okay, thank you very much for the presentation. Is there any question for this presentation? So may I ask about the load, the lamp load. What is the power of the lamp? I cannot hear you.
Sorry. Attention use.
What? Hello. Please unmute. We cannot hear you. So can you unmute your microphone? I'm not sure if there is any problem with the microphone. It seems to be the issue with the microphone. So we cannot hear you properly. Okay. Unfortunately. All right. So that's fine. That's okay. So there is another option. Okay, this is our last presentation, so maybe that's fine to wait a little bit for the answer. Yes, I think this seems to be working well. Hello? Doesn't work. Anyway, we are running out of time, so maybe I just want to thank you everybody to joining this session. Thank you the presenter for present us some very interesting work. So before we conclude the session, may I ask for a group snapshot? May I ask the presenter to turn on the camera so that we can take a snapshot for our session before we leave and join other session? Right? If still here, or everybody in this session, if you can turn on the camera, please, so that we can have a snapshot together. Right. So thank you very much. ECTICon will continue until 27. So I hope that you can join other session and have a discussion in very variety field of electrical engineering and electronics. Okay, so thank you very much for your attendance and see you in the next section. Thank you.
Good afternoon. I'm not sure that my voice is clear enough. Hello. Hello.
I can't hear you, Kerry.
Okay, I think we are about to start because it's just it's 2:45 already. So I'm going to start this session for the 19 ECTICon for this year. So we are going to have 5 papers from 5 presenters. The first paper that we are going to start is high performance grid tie 3-level T-type converter for off-board battery chargers under AC side voltage distortion and unbalance. This paper authored by Thidarat Thanakam and Yuthana Kamsuwan from Department of Electrical Engineering, Faculty of Engineering, Chiang Mai University, Thailand. So we are going to see the performance of a three-level T-type converter under the conditions of distorted and unbalanced grid voltage for the off-board battery chargers. So, Kun Thidarat, are you ready to present?
Yeah, I'm here in the room. Good afternoon, everyone. I'm Thidara Thanakam. I'm a presenter.
Okay.
And Professor Yuthanakan is a corresponding author. We are from my
you have
university.
15 minutes for
Today, I'm going to talk about
presentation
a high-performance
just about
T-type converter
just about
for off-board
one or two
battery chargers
questions
under
after
the AC side
that.
voltage,
Let's start.
distortions, and unbalances. There are 4 topics for presenting today. Firstly is background and main drawback, giving you in detail of the off-board battery charger system and unusual grid voltage,
So I'm sure I can see
which
any screen.
adversely affect charger operation. That brings to the second topic, is a proposed control system under AC
I'm sure
voltage,
for
distortion, and unbalance.
presenting now
Then the simulation results are provided
because I did not see
to
anything.
verify the proposed control system operation in both of AC side and DC side.
Can you see the video presentation of the country?
Yes, I can.
I cannot see. I see nothing.
What about
Just the list of.
the? Okay, I will share.
I see the presentation.
I can see.
But I cannot see from my side. I don't know what happened with with my network.
I try to fix it. Okay, could you see it, Professor?
Yes.
Okay. Okay.
I got it.
Okay, I will start it again.
Okay.
Battery. Good afternoon, everyone. I'm Thidara Thanakam. I'm a presenter. And Professor Yuthanakan is a corresponding author. We are from Chiang Mai University. Today, I'm going to talk about a high-performance grid-tied T-level T-type converter for off-board battery chargers under AC side voltage, distortions, and unbalances. There are 4 topics for presenting today. Firstly is background and main drawback, giving you in detail of the off-board battery charger system and unusual grid voltage, which adversely affect charger operation. That brings to the second topic, is a proposed control system under AC voltage, distortion, and unbalances. Then the simulation results are provided to verify the proposed control system operation in both of AC side and DC side. And the last one is conclusion. Let's start at the background and main drawback. Here show you the background of the off-board battery charger system. It can transfer high power rating of DC charging due to a large infrastructure. So it's appropriate for fast charging. The off-board battery charger configuration is divided into 2 parts. There are a power part and a control part. In the power part, it consists of a three-phase git voltage source, a converter, and a battery pack. The key point is when the git voltage is short or unbalanced occur like this. The control system won't be able to detect a correct angle position of the git voltage like this figure. As a result, the system can control the charging and can absorb sinusoidal current. So this work has proposed a control system of a charger to support the operation when the unusual git voltage occurs. This is a configuration of work. The main highlight is this block. It consists of a proposed alpha beta PLL algorithm, a standard current control, and constant current and constant voltage mode. When the git voltage is short or unbalanced, the proposed alpha beta PLL algorithm will prove the git angle to correct, which perform a linear angle that operate under the standard current control by choosing CC or CV mode in operation. If you don't have this algorithm, absolutely, you can get a correct angle position, which brings through the sinusoidal current. This control is applied for T-type converter. The T-type converter is a multi-level converter. It benefit of lower switching loss, less EMI, and better waveform quality when compared with a two-level converter. It has performance equivalent to NPC converter, but just required for 12 switches. In the next slide, I will talk about the step operations. There are 4 steps that operate when the git voltage distortion or unbalance occur. The first step will measure the phase git voltage in terms of V alpha beta G and send them to step 2. The step 2 is a key point of the operation. It's developed from a conventional alpha beta PLL algorithm by applying the standard PLL at here to obtain a correct angle position on theta C palm. It performs a linear angle and can obtain a new voltage signals V alpha beta C and VDVQ. The operation starts from comparison between V alpha beta G and feedback signals to find some error. Then the error will pass through a PI controller to obtain a new angle. This angle used to generate the new voltage signals, which correspond to a fundamental value. After that, the standard PLL will be put here to make more accuracy angle position. This signal will be used in the standard current control of step 3. In the step 3 can control under CC and CV mode. In the step 4, will receive the reference voltage to control switches of the converter by generating signals through PWM technique. Moving to the simulation results. The parameter values of this system shown in this table. In the AC side, we provide control system operation results to verify the correctness of the git angle and the git current that operate under CC mode at SOC 20% and CV mode at SOC 90%. In each mode is considered as 3 case study, namely case A1, case A2, and case AT. Case A1 is the ideal gate voltage condition. Case A2 is the distorted and unbalanced gate voltage condition. And case AT is the distorted and unbalanced gate voltage condition with the proposed algorithm. In each case, will be compared in the comparison result. While in the DC side, show you in result of battery charging to verify the feasibility of the charger. Let's see control system operation. Case A3 in both of CC mode on your left hand side and CV mode on your right hand side. You can clearly see that even gate voltage distort and unbalanced. The proposed algorithm can generate B alpha beta C which have amplitude equal to the nominal voltage and can generate the beta C path which perform as linearity and brings to the sinusoidal current waveform. However, the CV mode shows that is not appropriate response for the low charging current because THDI was increased. This slide shows the result of battery charging. Here, the x-axis is SOC and the y-axis are battery voltage and battery current. This red line of case A3, it performs like case A1, which the voltage and current can be controlled following commands. So this system has feasibility for charging. Besides that, THDI of phase A in each case of the T-type converter shown in this figure, and compare with a NPC converter as well. You can see that THDI of red line in case A3 is less than case A2 or the gray line. Moreover, the red line still correlate with yellow line. The yellow line is NPC converter. So the proposed control system of the T-type converter has better THDI than a conventional system and has a performance equivalent to the NPC converter as well. To sum up, the proposed controller is used in the T-type converter based off-board battery charger. It operates under CC and CV mode, which found that this system gives a high performance such as can control voltage and current of charging, can correct the power factor correction, and correct the gate angle. And the gate currents are almost sinusoidal waveform under ACI distortions and unbalances. That brings me to the end of my presentation. Thank you for your attention.
So, thank you very much, Ms. Thidarat, for your presentation. So, now it's time for question or any suggestion. Any question from the panel?
May I have a question?
Please.
I have a question about the off-board charger. Do you mean that we have to remove the battery out from the car and charge, or we have the overriding process to override the onboard charger for the charging.
So, Mithidalat.
Yes. Could you ask it again, please?
Your research is the onboard charger. When you want to charge the battery, you have to remove the battery from the car, or you have the way to override the onboard charger of EV.
Oh, yes. The battery is stay in the car, and the off-board charger is outside, and send the DC power to the battery. We not use the onboard charger.
And I think on the EV have the charging controller, DC charge controller in the car. And how we override this controller.
Hello.
Did you mean in the car have the DC charge?
Yeah, but the input of the onboard controller is the DC.
Yes.
Yeah. You mean you are not the charger, but you are the DC supply for the charger. That's right.
The input of onboard charger is AC.
Yeah, every battery have the charging controller, and you feed the DC for the car.
Yes.
Yeah, and your work is the DC supply. That's right.
Yes.
Okay. Now I think I understand because I have some confused about the charging controller.
Okay. So, thank you very much for the question, and also Ms. Thidalat. I think we are running out of time. We have reached over 15 minutes. So, thank you again, Ms. Thidalat, for your presentation, and also thank you also for the participation of our audience. So I would like to move to the second topic. The title is An Analysis of Potentials and Economic Benefit of Distributed Generation as Reactive Power Provided in Thailand. This paper prepared by Puvasalan Pisut Saingam Surapat Lab Visut Tisarod and Surachai Chaitasani from Department of Electrical Engineering, Faculty of Engineering, Chulalongkorn University, Bangkok, Thailand. So, Ms. Puvasalan, Kun Puvasalan, are you ready to present?
Yes, I'm here.
I'm sorry if I if I read your name not so correct, so maybe you can correct me.
It's Mr.
Okay.
Puvasalan Puthanger.
Here we
Yes,
are.
Mr. is correct.
Puvasalan. Okay, okay. So if you are ready, you can start now.
Hello everyone and welcome to my presentation. My name is Puvasalan Puthanger. Today I'm going to present you an analysis of potential and economic benefits of distributed generations and electric power providers in Thailand. The outline of this presentation consists of 5 items. The first one, introduction, will discuss about the background and the objective of this study. The second one, electric power source, will let us know which device can provide electric power. The third one, electric power cost model, will let us know how to allocate the electric power cost. The fourth one is my proposed selective power analysis model to study the economic benefits when DG support the electric power. The fifth one was results and discussions, and the last one, conclusion. The introduction of this study will discuss about the structure of the electricity grid and the ancillary service. The traditional power grids are vertically integrated structure which comprised of 4 systems: generation, transmission, distribution, and consumers. And conventional generators connected to transmission network have a duty to produce electric power to consumer. Apart from that, they also provide security and reliability service to the system in terms of power balancing and voltage support. In the past, both energy producing and ancillary service costs are bundled and recovered through electricity tariff. However, nowadays, the power grid structures are more likely to change. The idea of open access in electricity network is proposed to encourage the competition in business, and the cost of DG or distributed generation technology are lower. Thus, the number of DG are increased, and the reliance on the conventional generators are reduced, which cause the reduction of the ancillary service. Therefore, the DG are proposed to be the new ancillary service providers of the system. Since the ancillary services are becoming valuable and limited, the bundle tariff would not be fair for the providers. The cost of ancillary service should be separately recovered from the energy service. And this study only focuses on the electric power services. The objectives are to investigate the potential of DG in Thailand to become electric power providers and examines the economic benefits of DG for electric power ancillary service. Before anything else, we have to know that each device can provide electric power. Electric power sources can be categorized into 2 groups: static electric power sources, dynamic electric power sources. There are many electric power sources, for example, SVC, STATCOM, condenser. However, in this study, we only discuss 3 electric power sources. The first one, capacity banks. Capacity banks are the main static electric power sources of the system. They have low investment cost, simple installation. However, they generate enough current and easily export in a high temperature. The second device are synchronous machines. Synchronous machines are the main dynamic electric power sources for the system. They have electric power and voltage to control the electric power, and they can provide electric power in generation mode and condenser mode. To support electric power, synchronous generator require additional capacity, which lead to the additional cost considered as a lost opportunity cost. The last one, inverter, Inverters have high potential dynamic negative power sources. They are necessary for renewable energy sources, and they have many functions for negative power control. And just like synchronous match generators, inverters require additional capacity for negative power service. And the additional cost, which considered as a loss operating cost, should be properly allocated to recovered by the negative power tariff. So the next thing I'm going to talk about is how to allocate the negative power cost. Some negative power sources can produce both active power and negative power. In the regulated electricity market, negative power costs should be considered and allocated separately from active power. So many studies propose the idea of a negative power cost model. The first method is triangular approach. Triangular approach is a method for estimating negative power operational costs using a quadratic equation. The equation is converted from an active quadratic equation using the properties of the triangle. The equation of the negative power cost are shown in this equation. The next method is opportunity cost-based approach. Opportunity cost-based approach is a method for estimating negative power investment costs. To support negative power, it requires additional installed capacity. The additional costs for negative power service are considered as a lost opportunity cost, and that additional cost should be recovered by the negative power tariff. After knowing some background about negative power, the next thing I'm going to tell you is about my proposed model. The first thing we have to know is how much DG is connected to the network. Since every generator has to register that information to the Energy Regulatory Commission, trust the information on installed capacity of DG can be searched on the Energy Regulatory Commission's database. And in the connection code of MEA and PEA state that DG will be able to adjust the negative power within the prescribed range. With this information, we can approximate the amount of negative power from DGs that can provide to the system. And in order to calculate the payment of the negative power service, the negative power rate is necessary, which is done on step 2. To determine negative power cost, the average cost of each negative power source is studied from the negative literature. Then the costs are allocated, consider the loss opportunity cost and power factor, and then the negative power costs are divided by the negative energy of each source. So the negative power rates of each study are shown in this equation. After studying the rate, another important thing we have to know are the amount of negative power from each source. It can be calculated from the network model with the silent program. The first scenario is when conventional generators are the main negative power providers. The payments for negative power service are calculated by multiplying the negative power with the rates that we paid earlier. And in another scenario is when DG support the system in negative power service. But the amount of negative power from DG are limited by the voltage constraints. They cannot provide at their full capacity, but they help reducing the demands of negative power at their connection points. So the negative power from conventional generator is changing, and the payments of this scenario are calculated and compared with the first one. The results show that negative power rate of inverter-based DG are lower than the others. The overall available negative power from DG that reserved for supporting the network is more than 3,000 MVAR. And in the second scenario, DG can provide negative power to the system. However, the amount of negative power as shown in the red bar are limited by the system constraint, while the overall available negative power are shown in the green bar. On the left table, the amount of negative power from conventional generators are changed due to the support of the DGs. The payment in a situation when DG help providing negative power are shown on the right table. It can reduce the total negative power payment, which might reduce the tariff that users have to pay for this service. In the conclusion, the DG connected to the networks in Thailand have a high potential to provide negative power. However, due to the voltage limit of this study model, only 10% of total available negative power from DG can provide to the system. The system operator should solve the problem by reducing the reserve or improve the system to receive more negative power from DG. And system operator should prioritize inverter-based DG for negative power service because they have a lower negative power cost than the machine-based. And thank you for your attention. If you have any question, you can ask me now.
Thank you very much, Mr. Puvasalan, for your presentation. So now it's time for question or any suggestion that you want to share, please. Are there any questions from the floor? So that is a very interesting study that you focus on the potential of distributed generation in Thailand to become like a reactive power services. And Mr. Puvasalan, I would like to you to explain again about the normal scenario and the second case. What is the difference? What is the criteria for normal scenario that you mentioned?
Yes, in a normal scenario is when we rely on the conventional generations for reactive power service, and we didn't get anything from the distributed generations. But in the second scenario, we prioritize on the distributed generations for reactive power service. As the reactive power from DG is provided to the system, so the reactive power from conventional are changed. Yes, this is a difference in two scenarios.
Okay. So according to your study, what is your recommendation? Maybe you can explain to us again about the distribution operator or system operator, what they should be considered or how they can deal with such kind of these services.
Yes, I would like to recommend something. I think there is no management in reactive powers in distribution network nowadays, and I think it is necessary because reactive power shouldn't provide from the long distance as it is for nowadays, because we receive from the conventional generation, it should be DG instead. So, and according to my study, the cost of reactive power from DG is very low. So, and they have very high potential. So if we can manage them, if we can have a the system operation or the communication for this service, it might be good for the system. Yes.
Especially from invertebrate distributed generation, right?
Yes, yes.
Okay. So is there any additional question from the floor? So let me check. Okay, this is about time. This is we are running out of time now. So thank you very much, Mr. Puvasalan, for your presentation.
Thank you, Dr. Shanit, and thank you everyone for your attention.
Okay, so we are moved to the third one, that is an analysis of base electricity tariff reflecting varying chart in Thailand. This paper authored by Pulin Kamsuwan and Sulapat. Okay, so it seems to be the same group. Sulapat, Labisut Tisarod, and Surachai Chai Usani from Department of Electrical Engineering, Faculty of Engineering, Chulalongkorn University. So I think that Kun Purin will be the presenter, right?
Yes, I'm here.
Okay, if you are ready, we can start now.
Okay. Hello, everyone. My name is Purin Kamsuwan, an electrical engineering student from the Faculty of Engineering, Chulalongkorn University. Today, I'm going to present my research on the topic and analysis of base electricity tariff reflecting wheeling charge in Thailand. This presentation will cover the 6 topics, including introduction, purposes, wheeling charge, calculation algorithm, result and discussion, and conclusion. The electricity tariff structure in Thailand is defined as a uniform tariff, which is divided into 2 rates. Firstly, wholesale tariff, the tariff of electricity sold by the Electricity Generating Authority of Thailand, or EGAT, to the Electricity Distribution Department, namely the Metropolitan Electricity Authority, the MEA, and the Provincial Electricity Authority, the PEA. And the second, retail electricity tariff, the tariff of electricity sold by Electricity Distribution Department to people and by EGAT to its direct customers. The wholesale tariff consists of 3 parts: the wholesale-based electricity tariff, the wholesale variable electricity cost, and the value-added tax, or VAT. The retail tariff consists of 3 parts too. It is the retail-based electricity tariff, the retail variable electricity cost, and VAT. From the past slide, Thailand charged the same electricity rate throughout the country, which could not be identified and does not reflect the actual financial status of the electricity authorities, such as the cost of the generation system, transmission system, and distribution system. In the future, private companies could participate in the power purchase market, causing the revenue of electricity authority to decrease. As a result, the electricity authorities have to charge more for electricity customers to cover past costs and operation costs in the future. However, the private companies needs to use the system of electricity authorities, so they must pay money for their use. In this paper, it is called the wheeling charge. The purpose of this paper is to study the costs involved in the electricity business, to calculate the revenue requirement that electricity authority receive from electricity distribution and the wheeling charge, and to calculate the base electricity tariff that the wheeling charge revenue is used to offset in order to relieve people's electricity expenses. A wheeling charge is an energy system service rate that is charged when the government authorizes direct electricity trading between power producers and consumers, utilizing the electricity authority's transmission line. The wheeling charge is calculated using three main methods. Firstly, embedded cost. This method is divided into four sub-methods, namely postage stamp method, contract part method, distance-based megawatt-mile method, and power flow-based megawatt-mile method. The second, incremental marginal cost, is divided into the following methods: short-run marginal cost, long-run marginal cost, short-run incremental cost, and long-run incremental cost. And the third is hybrid mode. This study illustrates the calculation of the wheeling charge using postage stamp method, as it is considered as easy to calculate and understandable method. This slide presents an overview of the base electricity tariff and wheeling charge calculation, which are the same. Let's start by calculating the revenue requirement from operating income plus expenses, where operating income is calculated as net operating profit after tax, or NOPAT, divided by 1 minus the percentage of tax, and the NOPAT resulting from taking total assets multiplied by the percentage of ROIC, or return on invested capital. Expenses are calculated from operation and maintenance expenses plus depreciation. This slide is a detailed step-by-step calculation, starting from the calculation of the base electricity tariff and the wheeling charge using postage stamp method. Step 1. Calculate under construction and post-construction after COD. Step 2. Determine total expenses and cash flow assets. Step 3. Determine the annual total asset. Step 4. Calculate revenue requirement. And the last step is to calculate the base electricity tariff on the flow chart in the last slide. In the case of third-party assets, or TPA, power demand will decrease as people turn to purchasing electricity from private company. Step 7 is to calculate wheeling charge revenue. And step 8 is to calculate the base electricity tariff with wheeling charge revenue factored in. This is the result of the base electricity tariff in different cases and the wheeling charge revenue. In the first column is the base electricity tariff in standard case. The second column is the base electricity tariff when power demand decrease, which show that the base electricity tariff is higher. The third is the wheeling charge revenue, calculated by the base electricity tariff in the first column multiplied by the power demand that people buy from private sectors. And the fourth column is the base electricity tariff from which the wheeling charge revenue is compensated for the revenue requirement. The result is the base electricity tariff decreased from the second column, or return equal to the first column. That brings us to the end of presentation. I would like to summarize by saying that the intervention of private companies of TPA is considered a significant change that directly affects electricity authorities in terms of the lower amount of electricity use, while the total costs remain constant. Consequently, the base electricity tariff shall be charged in a higher price. The wheeling charge, therefore, is considered a suitable solution to manage the increased base electricity tariff. The revenue from the wheeling charge shall be utilized to reduce the revenue requirement of the distribution systems, namely the MEA and PEA, allowing users to pay a lower price for electricity. This is the end of my presentation. Thank you so much for your interest and your attention. I sincerely appreciate that I've had this opportunity to present to you. Thank you. I think you mute the microphone.
Okay, so sorry. Thank you very much, Mr. Pulin, for your presentation. So we have just one or two questions from the floor. Is there any question? Okay, while waiting, I have one question. Mr. Pulin, and can you explain what is the reason why the result of the study, I mean the electricity tariff, different in different part? For example, the different region that PEA are responsible for, because the base electricity tariff, they are quite different. For example, the table 2, or I'm not sure, maybe yes, mini table. Mr. Pulin.
Do you mean that the different amount of tariff
Yeah, that's right. For example, the base electricity tariff will decrease per demand, but in different zone or different region, they are quite different. So do you know what is the condition, or what is the reason why they are quite different?
Can I ask for my clearly question?
I mean, for example, the base electricity tariff with decreased power demand, or maybe for example, the table number 5, the base electricity tariff with billing charge revenue. Okay, for example, so you can see that the this value in different region, for in north or northeastern or central, or they are quite different. So what is the reason? What is the condition why these chart are quite different?
In the same column, right?
Yet in the same column.
Okay, I would say that because the cost of each region is different. Also, the power demand that the PEA sent for distribution for each region is different too. So when I calculate the base electricity tariff, that use the cost like for construction, generation, transmission, and distribution, something to calculate with the power demand that each region sent to the people. That's why for each region they have a different base electricity tariff.
Okay, good. So this is why I just want to emphasize that this is quite a fair methodology to pay for electricity tariff in the near future, because in different area, as you already mentioned, as you already explained. So we just wait for the regulation. Okay, so I'm not sure that is there any one question or any comment that the floor want to share. If there is no, I think it's about time. So thank you very much, Mr. Poulin, for your very interesting topic.
Thank you, Dr. Kanjit. Thank you, everyone.
Okay. So we move to the fourth one. That is the optimal sizing of hybrid energy sources for an islanded system using arbitrariness gray wolf algorithm. This will be presented by Mr. Surapon Gigsilisin, Department of Organization Innovation, Metropolitan Waterworks Authority, Bangkok, Thailand. Mr. Surapon, are you ready?
Yes, I'm ready.
Surapon. Okay, so it's your time.
Good afternoon, ladies and gentlemen. My name is Sorapon Kitsilisin. I am working as an engineer at Metropolitan Waterworks Authority, Thailand. Today, I would like to present you my research. The title is Optimal Sizing of Hybrid Energy Sources for an Islanded System Using Arbitrariness Gray Wolf Optimizer. This slide shows you the content of this presentation. First of all, I would like to show you the overview and research contribution. Mahasawat Water Treatment Plant is Thailand's second largest water production plant. It has the capacity of quality water production around 1.6 million square meters, and it has responsibility to produce the quality water to people living in Bangkok, Nonthaburi, and Samut Prakan provinces. Nowadays, Mahasawat Water Treatment Plant comprises the 4 phases for water production. The maximum electrical consumption is 20 megawatt. At present, Mahasawat Water Treatment Plant receives the electricity from the external sources. That causes high electricity cost and the ability to manage electricity by itself. This slide shows you the research contribution. First, studying the power system of Mahasawat Water Treatment Plant as an islanded system, I employ the hybrid energy sources for electrical supply, such as solar photovoltaic, wind turbine generator, diesel generator, and battery energy storage system. Then I developed the Gray Wolf Optimizer to have the better performance, so-called arbitrariness gray wolf optimizer. I will call it APVO. Then I apply the APVO to minimize the annual cost as the objective function of this study. Then I would like to show you the definition of gray wolf optimizer. Gray wolf optimizer is inspired by mimicking the behaviors of gray wolf in nature. In nature, when gray wolf see the prey, gray wolf will encircle around the prey before hunting it as a food source. Gray wolf have social dominance by separating into the 4 groups: alpha group, beta group, and delta group. Each group has its own leaders. I would like to call the leader alpha, leader beta, and leader delta. The leader alpha has the better fitness value among all the leaders. The another characteristic of gray wolf is that wolf can move toward the prey. I would like to call it the exploitation state. Also, wolves can move outward from the prey. I would like to call it the exploration state. This picture shows you the location of wolf, the leader alpha, leader beta, and leader delta. When wolf updates its position, wolf will observe the position of all the leaders and take the average position of all the leaders to be its new position. The updated position of a wolf can be calculated by using this equation. However, there are many drawback features of gray wolf optimizer. First, all wolves must depend on the position of all the leaders to update their position. That causes gray wolves are adhered to all the leaders and cannot export the excellent prey over the third space. Also, the balance strategy of gray wolf optimizer is not good because it can be seen in this figure. X-axis shows you the number of iterations and y-axis shows you the value of the absolute A. When the number of iteration increases, the value of A will decrease. It can be seen that when the number of iteration increases, the exploration state will by wolf to be raised. There is no guarantee for wolf to be in the exploration or exploitation state. This is a drawback feature of gray wolf. In order to overcome these issues, this study proposes arbitrariness gray wolf optimizer or APVO. Wolves can follow the random wolves including all the leaders, leader alpha, leader gamma, and the leader beta for updating their new position. This study determines the number of random wolves to 3. This is the equation for the finding out the number of random wolves. Then the updated position of a wolf can be calculated by using this equation. Also, this study proposes the balance strategy between the exploration state and the exploitation state by using the iteration number, a random parameter, and a criteria. I would like to give you an example case. This is the case 1. The number of random wolf is 1 or wolf 1. This is the location of wolf, location of prey, and location of wolf 1. Wolf will move toward to this wolf in order to export the excellent prey over this area. Example case 2. The number of random wolf is 2. In this case, is the leader alpha and wolf 2. This is the location of the leader alpha and the location of wolf 2. Wolf will move to this area to discover excellent prey over this space. Example case 3. If the number of the random wolf is 3, in this case, it is the leader delta wolf 2 and wolf 3. Wolf will move to this area to discover excellent prey over this area. And case 4, the number of the random wolf is 3. Wolf 1, wolf 2, and wolf 3. Wolf will move to this area to discover excellent prey over this area. So ACVO is to allow wolves not to adhere to all the readers for updating their position and have many opportunities to discover excellent prey over the search space. Also, this study proposes a balanced strategy for the exploration state and exploitation state. This is a wolf eye or a wolf. If the number of the iteration is less than the half cost of iteration or equal to the half cost of iteration, and the random value is less than or equal to 0.5, this wolf will use the concept of ACVO or the exploration state. Otherwise, this wolf will use the concept of gray wolf optimizer or exploitation state. Beneficially, the exploration performance increases and the premature convergence is eliminated. This slide shows you the objective function optimization for hybrid energy sources. This is the equation of calculating the output power generated by wind turbine generator. Wind turbine generator output power depends on the wind speed. For PV, the power of PV generated by PV panel depends on the solar irradiance, temperature, and efficiency. This equation shows you the fuel cost of the diesel generator. For battery energy storage system, this study uses the state of charge or SOC. And there are many constraints in this research, such as the power balance, SOC, and the number of wind turbine generator, the number of PV, and the number of battery energy storage system. The objective function of this study is to minimize the annual cost. The annual cost comprises the capital cost, maintenance cost, fuel cost, and penalty cost function. For the maintenance cost, is the summation of the maintenance cost of wind turbine generator, PV, and diesel generator. To oversee the performance of ACVO, the results of ACVO will be compared to the iterative search algorithm, source swarm algorithm, and gray wolf optimizer. This slide shows you the power consumption of the Mahasawat water treatment plant. This is power consumption in a summer day, solar irradiance, and wind speed. This slide shows you the results of this presentation. This figure shows you the results of the number of the wind turbine generator, PV, and battery. It can be seen that all optimization algorithms provide the same number of wind turbine generator and battery. However, the number of PV is different from each other. This slide shows you the total generated power of diesel generator. ACVO provides the highest total generated power. For the total annual cost as the objective function of this study, ACVO provides the greatest total annual cost over the total annual cost of the other optimization algorithm. Conclusion. This study proposed arbitrariness gray wolf optimizer or ACVO developed from gray wolf optimizer. Wolves are not adhere to all the readers for updating their position and can randomly follow the position of all wolves over in the search space for updating their position. The exploration and exploitation performance of ACVO are balanced by using random parameter and criteria that encourages premature convergence will be eliminated. Hybrid energy sources comprises wind turbine generator, PV, and battery, and diesel generator to be employed to the power system of hybrid of Mahasawat water treatment plant as a case study. The objective function is the annual cost comprising the capital cost, maintenance cost, and fuel cost. It can be seen that ACVO obtained the best annual cost over the annual cost by the other refer optimization algorithm. Thank you very much for your kind attention. Please feel free to ask me any question. Thank you so much.
So thank you very much, Mr. Salapon. That is also another interesting research. Is there any question or suggestion from the floor? Okay, while waiting, Mr. Salapon, I have one point that I would like to ask. I saw that when you mentioned about maintenance cost, when you are considering the maintenance cost, we have just three costs that include in that. It's like from wind turbine, PV, and diesel gen. What about the BESS? What is the reason why you are not including this in the maintenance for the maintenance cost?
Yes, thank you very much for your question. For the maintenance cost of the battery energy storage system is ignored because Mahasawat water treatment plant is using the free maintenance battery energy storage system. I'm not if I can remember it, lead acid battery. I'm not sure. So in this research, that's why I ignore the maintenance cost of the battery energy storage system.
That means in case if we are considering another site that they use like such kind of energy storage, that they need to we need to do a kind of maintenance, we have to include that in this condition as well, right?
Yes, definitely. Other plants can use this equation for calculating the annual cost and can adjust the equation to be suitable for their plants to increase, for example, to increase the maintenance cost of the battery energy storage system.
Okay, good. So maybe the last question. This seem to be that like kind of optimization of the off-grid system, right? Islanding. So what is your opinion that if we need to use in like kind of an on-grid system?
Oh yes, thank you very much for your question. In this research, I consider the off-grid system, but now I'm studying the power system of Mahasawat water treatment plant as a on-grid system. So I'm conducting research right now, and
okay.
the results will be concluded soon.
Oh, okay. That we are looking forward to see describe that at that future work that you are going to deliver.
Thank you very much.
I think it's about time that we are going to finish the fourth paper from Mr. Salapon from Metropolitan Water Works Authority. I would like to move to the last paper. Actually, I just knew that we have 5 paper in this session, so I'm not sure if I'm wrong with the title. You can correct me. The last one is the implementation of an Class B voltage source inverter for domestic medical application. So maybe the presenter should introduce yourself a little bit because I didn't have your information in my hand now. I'm so sorry about that. So, are you ready? The fifth one.
I'm here.
Okay. So, it's your turn.
Good afternoon, Chairman and everyone. My name is Samat Yatchankhabu from Rajamangala University of Technology, Lana, Chiang Mai. Today, I would like to present my paper. The paper title is Implementation of Hybrid Class D voltage source inverter for domestic medical application. Nowadays, induction heating is one of the methods that is widely used in many applications, such as industry, automotive, home appliance, medical. Past research have been focused on induction coil design, high efficiency inverter topology, and control and switching schematics to achieve high efficiency and energy saving by using resonant inverter, which can be classified as voltage source inverter and current source inverter. Recent development in switching and control strategy have made the voltage source inverter popular due to its output power control capability under the zero voltage switching operation, so-called CVS condition. This slide shows the block diagram of an induction heating system. A typical induction heating system includes a power supply, impedance matching transformer, and resonance tank. A power supply includes two major sections, rectifier and inverter. The induction coil is a part of the resonance tank. The induction coil can be modeled as resistor and inductor in series or in parallel with a resonant capacitor. This paper presents a Cardi voltage source inverter employing a half-bit series resonance circuit, focusing on the benefits of a resonant coupling and temperature time for nanoparticle heating process to create technology and innovation for supporting the research and development process in domestic medical application. The heating process is associated with heat transfer by conduction and convection. The output power of the inverter can be controlled by adjusting the switching frequency with the fixed duty cycle to maintain CVS condition for maximum power transfer under load condition of the high quality factor. In the heating process for nanoparticle research, the required temperature depends on the type of substance used, the temperature level, reaction time, solvent type, and the deterioration period are adjusted according to the design size and shape. Picture 2a shows the typical circuit configuration of the proposed system employing a half-bit Cardi series resonance circuit. The inverter consists of two IGBT with antiparallel diode. In this case, the effect of parasitic inductance and capacitance in switches are neglected. An equivalent circuit model of the matching transformer and RLC resonance tank is shown in picture 2b. The equivalent inductance, resistance, and capacitance are given as this equation. Then the resonance frequency and the quality factor are given as both equations. So we can determine the average output power from this equation. Picture 3 shows the gate signal and typical steady state waveform of the inverter output voltage and output current. If the quality factor is sufficiently high, so greater than 2.5, the inverter output current is a sinusoid or uphill sine wave, whereas the output voltage is a square wave, and the inverter output current is lagging the output voltage by the phase angle theta. In this case, all switches will turn on in sub-switching condition during switching transition, whereas the Modes of operation are described in 4 states, as shown in picture 4. So, the prototype of the resonance tank implemented in the laboratory is created as shown in picture 5. We use the helical coil made of a hollow copper tube, which consists of 7 turns. In this study, we use water as a sample for testing. The sample is placed in the test tube, which is placed in a beaker of water. Furthermore, the heat depends on the amount of the induced current on the secondary side or in the induction coil. The heat is transferred to the sample by convection and conduction. The inverter specification and circuit parameters are given in table 1. The R coil and L coil in table 1 are experimentally measured with LCR meter. So we can calculate the equivalent resistance, inductance, and capacitance as shown in this slide. The resonance capacitor of 6.2 microfarad have been selected to provide the resonance frequency as 46.5 kHz, and the quality factor is approximately 27.6. A hardware prototype is created in the laboratory as shown in picture 6. The proposed control system have been implemented in hardware using the DSP controller to generate the getting signal for all switch, induction coil, and impedance matching transformer, and the inverter board. This slide shows the simulation result and experimental result using parameter in table 1. For the complete CVS condition, the inverter must operate as the switching at the frequency slightly higher than the resonance frequency. So the switching frequency is set to 47.5 kHz. Picture 7 shows the simulation result at the switching frequency of 47.5 kHz. Picture 7a shows the inverter output voltage and output current waveform, whereas picture 7b shows the switch voltage and switch current waveform. For experimental result under the design CVS condition, the switching frequency is also set to 47.5 kHz, providing the inverter output power of 330 watt and achieving overall efficiency of 95%. The inverter output voltage and output current waveform are shown in picture SA, whereas the switch voltage and switch current waveform are shown in picture SB. In this experiment, the measurement are carried out at a room temperature of 26 degrees Celsius. The sample temperature is measured using the glass thermometer to reach the temperature of 90 degrees Celsius for 650 seconds, as shown in picture 9 and picture 10. However, we have some limitation in this work where the AC input voltage can only be set as 110 volts due to load current limitation on the secondary side. Conclusion: this paper presents the hardware implementation of a high-capacity voltage source inverter applied to nanoparticle heating process for medical application by using combined heat transfer between convection and conduction. The inverter operates slightly higher than the resonance frequency to maintain CVS condition under the high quality factor, resulting in reduction of the switching loss for improving the efficiency. Moreover, the rated output power of the inverter is about 330 watts, with an overall efficiency of 95%. The experimental results show that the sample is heating up to 90 degrees Celsius for 650 seconds. The validity of the proposed control system was verified to simulation result and experimental result. However, the limitation of work is also given for further investigation and applied to other diverse applications for the optimal temperature length of 30 to 70 degrees Celsius. Thank you very much for your attention.
So, thank you very much, Mr. Samad, for another interesting paper.
Yes.
We still have time for one or two questions or any suggestion from the floor, please. So, Mr. Samad, I have one or two questions. The first one is, can you explain to us again about, actually I am not get used to with the domestic medical application. So
Yes.
would you please explain to us again about the domestic medical application that we can see more picture of that?
Actually, the aim of this paper is to design and implement the voltage source inverter by employing the resonance circuit and induction heating technique to create technology and innovation for supporting the research and development process in domestic medical application. In this paper, especially nanoparticle research. And nanoparticle research is a process to use sample bottle containing the solution and magnetic nanoparticle.
Okay.
And the required temperature depends on the type of substance used or particle. Usually, the temperature range is about 30 to 60 degrees Celsius. Yes.
Oh, this is very interesting. So, do you have any plan for your future work?
Yes. This is we have some limitation on present in this slide on the road side because the load current is higher than the cable current rating. So I think that we can improve is by designing the load side, new load side in the future. I think it can take the input voltage of 30 volt for the Thailand.
Oh, okay. Okay. Thank you very much, Mr. Samad.
Thank you very much, Dr. Kachit.
So we are. Thank you. Hope to see you in next conference with our with other interesting topic. And so we are at the end of this session. We have very good topic from 5 presenters in various from various fields, but mainly in power system. So I would like to thank for all 5 presenters for this session, and also would like to thank for our participants and any question or any seconds that you put on that you just put on in this session. So on behalf of the 19 ECT Icon or ECT Icon 2020, I would like to thank everyone for joining this session and wish you to spend your time to attend other session. And we have I'm not sure on 26 there are many very interesting program on site. So see you. Bye bye.
Thank you ครับอาจารย์
Thank you. Bye
Thank
bye.
you